take a slow breath and let your eyes close if they haven't already. You don't need to follow anything. You don't need to hold on to a thread. This is just a quiet voice in the dark, talking softly about the night sky while you drift. There is nowhere to go, nothing to remember, nothing to solve. Just listen, the way you might listen to rain on a window, without needing to catch every drop. Think about the night sky for a moment. Not the one you see when you step outside and squint past the streetlights, but the deeper one. The one that sits behind the brightest stars, behind the glow of the moon, behind everything your eyes can catch. Picture the darkest stretch of sky you can imagine, a patch between stars where there seems to be nothing at all, a black velvet emptiness. Most of us, when we look up on a clear night, feel we are seeing a pretty full picture. Stars scattered like salt. Maybe the pale ribbon of the Milky Way if you are far from city lights. It feels like a lot. It feels like the universe is showing us most of what it has. But that feeling, as full as it is, turns out to be only a small part of the story. A very small part. Almost everything that actually exists, almost everything that makes up the universe, is not something we can see. Not with our eyes, not with the largest telescopes ever built, not with any instrument we have ever pointed at the sky. The stars, the planets, the glowing gas clouds, the dust lanes that look like dark rivers cutting through the Milky Way, all of that, all of it together, is just a tiny fraction of what is really out there. The universe is mostly made of things that are invisible. Things that give off no light, absorb no light, reflect no light. Things that move through space and through us without a single trace our eyes or cameras can catch directly. This is a strange thought, and it might sound at first like something out of a storybook. But it is not a story. It is one of the most solid, most carefully checked findings in all of modern science. Astronomers and physicists, working over many decades, with many different kinds of instruments and many different lines of evidence, have come to agree on a picture of the universe that is both deeply strange and deeply humbling. The ordinary matter that makes up you and me, and the chair beneath you and the pillow under your head, and every star in every galaxy we can photograph. That kind of matter, the kind we can touch and measure and understand, accounts for only about 5% of everything that exists. Just 5%. The other 95% is made of two things we call dark matter and dark energy. Two names for two great unknowns. Two labels for the invisible. Let those words settle for a moment. Dark matter, dark energy. They sound mysterious, and they are. But the word dark here does not mean sinister or frightening. It means simply that they do not interact with light in any way we can detect. They are dark the way a radio wave is dark to your eyes. They are dark the way the air in this room is dark, even though it is full of oxygen and nitrogen and the gentle movement of your own breath. They are present, they are real. They have enormous effects on the shape and behavior and fate of the whole universe, but they remain unseen. And so tonight, as you rest, we are going to spend some time with these invisible things. Not to solve them, not to explain them away, but simply to sit beside them, to let the mystery be a mystery, without needing to fill the quiet with answers. The story of dark matter and dark energy is, at its heart, a story about not knowing. It is a story about how much of reality lies beyond the reach of our senses and our instruments, and how scientists have learned to map the shape of something they cannot see by watching the way visible things move around it. It is a story that began almost a century ago with a Swiss astronomer looking at a cluster of galaxies and noticing something that didn't add up. And it is a story that leads, step by careful step, to the realization that the universe is not only expanding, but expanding faster and faster, pushed apart by something we still cannot name. There will be time to walk through all of that, but not all at once, not tonight. Tonight we take the first quiet steps. So let yourself sink a little deeper into wherever you are lying. Let the weight of your body settle into the mattress or the cushion or the floor. There is no rush. The facts will still be here, drifting past like slow clouds. I am going to talk for a while about what the universe is made of, and the strange truth is that most of what I describe will be invisible. Not because I am hiding it, but because that is simply how the universe is built. Most of it is hidden. Most of it is quiet. Most of it does not announce itself to our eyes or our telescopes. And yet it is there, shaping everything we see. Think again of that patch of dark sky between the stars. Now imagine that the darkness itself has weight. Imagine that the blackness is not empty, but full. Full of something that passes right through the earth and through your body without a whisper. Full of something that pulls on galaxies and bends the path of light. Full of something that is stretching the very fabric of space, slowly, steadily, in all directions at once. That is the universe we actually live in. Not the bright pinpricks of the stars alone, but the vast unseen ocean in which those stars float. The stars are like distant ships, their lights tiny and brave against an immense dark sea. And the sea itself, the dark between and around and behind the lights, that sea is what we need to talk about. Because that sea is not empty. It is the main thing. It is almost everything. This idea can feel very large, and it is. But large ideas, when you are lying still in the dark, can also be comforting. They can put your own small worries into a wider frame. They can remind you that not knowing is not a failure. It is the natural state of a small creature looking out at a very big universe. The universe does not owe us a full explanation of itself. It simply is. And we, being curious, being thoughtful, being the kind of creatures who look up at night and wonder, we have managed to learn a surprising amount about things we cannot even see. That is worth resting with for a moment, not as a problem to solve, but as a quiet fact to appreciate. Over the next little while, I will walk you through how we came to know about dark matter. We will meet the people who first noticed that galaxies were moving too fast to be held together by the stars we could count. We will follow the light from distant galaxies as it bends around invisible clumps of mass. We will descend into deep underground laboratories where physicists wait for a single particle to bump into a crystal or a tank of liquid xenon. And then we will turn to dark energy, the even stranger discovery that the expansion of the universe is speeding up, as if something is gently pushing everything apart. We will sit with the numbers that describe the cosmic recipe: 5% ordinary matter, 27% dark matter, 68% dark energy, and we will let those numbers hang in the air without rushing to explain them. And at the end, we will arrive at the edge of what is known and simply stop there, together, in the quiet. But all of that is ahead. Right now, in this opening moment, the only thing to hold in your mind is a single, simple image. The universe is like an iceberg. The part we can see, the bright part, the stars and galaxies and glowing nebulas, that is the tip above the water. It is beautiful and it is real, but it is only a small fraction of the whole. Beneath the surface, unseen, lies the great bulk of the iceberg, the dark mass that supports everything visible. And deeper still, in the water itself, there is a current moving everything, a current we cannot see, but can measure, a current that is carrying the whole iceberg forward. The visible tip is ordinary matter, the hidden bulk is dark matter, and the deep current is dark energy. It is not a perfect metaphor, no metaphor ever is, but it is enough to rest on as you drift. So let the iceberg float in your mind for a while. A mountain of ice, mostly hidden, drifting on a dark sea. The stars you can see are the sunlit edge of the visible part. And everything else, the vast majority of everything that exists, is the unseen shape beneath the waterline, silent, massive, holding the whole thing steady. That hidden shape is what we are going to explore, not by diving down to touch it, but by staying here, in the quiet, and thinking slowly about what it must be like. There is a gentle kind of freedom in knowing how much is unseen. If most of the universe is invisible, then the part you cannot see is not a failure of your eyes. It is simply the way things are. The dark is not empty. The dark is full of something we are only beginning to understand. And even our not understanding is part of the story. Even the questions without answers have a place in the long, slow telling of how the universe works. You do not need to resolve anything tonight. You do not need to hold on to every detail. You can let the words wash over you like water, taking what settles and letting the rest drift on. The facts will still be true in the morning. The stars will still be there, and so will the dark matter, and so will the dark energy, doing whatever it is they do while we sleep. Take another breath, as slow as you like. Feel the air move in and out. That air is made of ordinary matter, the same 5% that builds galaxies and trees and oceans. And passing through that air, right now, passing through your body, are particles of dark matter, if that is indeed what dark matter turns out to be. They do not bump into the atoms of your skin. They do not leave a trace. They move through you as if you were made of empty space, which, in a way, you mostly are. The atoms in your body are themselves mostly empty space, with tiny nuclei surrounded by clouds of electrons. And between those nuclei, through those vast atomic gaps, the dark matter slips silently, without friction, without heat, without a single signal. You are swimming in an invisible sea, even now, even here, lying still in the dark. And that is not a frightening thought. It is a quiet one, a companionable one. The universe is closer than you think, and far stranger and far gentler. We will begin the deeper story soon, with a man named Fritz Zwicky and a cluster of galaxies in the constellation Coma Berenices. But not yet. For now, just the iceberg, just the dark sea, just the slow, steady knowledge that you are part of a universe that is almost entirely unknown, and that this is not a problem to fix, but a reality to rest within. The not knowing is part of the calm. The mystery is not a gap to be filled, but a presence to be acknowledged. It sits beside you, quiet as a cat in the dark, breathing its own slow breath. You don't need to name it. You don't need to understand it. You only need to let it be there, while you drift a little further from the shore of waking. The sky above you, whether you are under a roof or under open air, is mostly made of things we cannot see or name, and that sky holds you. It holds your galaxy, your star, your planet, your body. It holds everything you have ever known in a vast, unseen embrace. Let that thought be soft. Let it be wide. Let it carry you toward the edge of sleep, where the words begin to blur, and the darkness behind your eyelids becomes the same darkness that fills the spaces between the stars. There is no difference, really. The dark is all one thing, and it is full. When you are ready, we will begin the next part of the story. But there is no hurry. The story will wait. The universe has been doing this for a very long time, and it can wait a little longer while you rest. The story has been waiting, and now it can begin to unfold, slowly, the way a flower opens in the dark, unseen, unhurried. We are going to step back in time now, back to the 1930s, to a place called the California Institute of Technology, and to a man whose name deserves to be spoken softly into the night. His name was Fritz Zwicky. He was a Swiss astronomer, a man who thought differently from many of his colleagues, a man who was not afraid to point his mind at problems that others found too strange or too difficult. And he was, by many accounts, a little difficult himself, brilliant and brusque, a man of strong opinions and sharp words. But whatever his manner, he had a gift for noticing things that did not add up, and in 1933 he noticed something very large that did not add up at all. To understand what Zwicky saw, you need to picture a galaxy cluster. Not a single galaxy, but a whole gathering of them. Hundreds, sometimes thousands of galaxies, all moving within a shared space, held together by the pull of gravity. Like a city of stars, each galaxy a single neighborhood, and the whole cluster a kind of vast metropolitan sprawl across the darkness. Zwicky was studying a particular cluster called the Coma cluster, named for the constellation Coma Berenices, where it sits in our sky. The Coma cluster is a rich cluster, meaning it holds many galaxies. It sits about 320 million light-years away, which means the light Zwicky was capturing in his telescope had been traveling toward Earth for 320 million years. A long, slow journey through the dark, just to fall onto the glass of a telescope in California. Zwicky was interested in how the galaxies in the Coma cluster moved. He measured their speeds, the velocities at which they traveled within the cluster. Think of a swarm of bees, each bee moving on its own path, but the whole swarm staying together. The galaxies in a cluster are like that. They move relative to one another, some faster, some slower. And the whole structure, the cluster itself, holds together because of gravity. The mass of the cluster pulls on each galaxy, keeping it bound to the group. Without enough mass, without enough gravity, the faster-moving galaxies would simply fly away. The cluster would dissolve over time, its members drifting apart into the empty spaces between clusters. So the speed of the galaxies tells you something about the mass that must be there to rein them in. The faster they move, the more mass you need to hold them. This is a simple idea, and it is based on the same physics that keeps the Earth circling the Sun, rather than flying off into interstellar space. Gravity and speed balanced against each other. Zwicky measured the speeds of the galaxies in the Coma cluster, and he found that they were moving very fast, too fast, given the amount of visible matter he could account for. He added up all the mass he could see, the stars in the galaxies, the glowing gas between them, everything that showed up in his telescope, and he calculated the gravity that all this visible matter could produce. The number was far too small. The visible matter could not generate nearly enough gravity to hold the cluster together at the speeds he had measured. The galaxies should have scattered long ago. The cluster should not exist. And yet it did exist. It sat there in his telescope, calm and whole, a great city of galaxies that by all rights should have flown apart. This was a serious problem, the kind of problem that keeps an astronomer awake at night. The numbers did not match the observation. And when numbers do not match what you see, one of two things is true. Either your measurement is wrong, or there is something you are not seeing. Zwicky trusted his measurements, and so he proposed that there was something else in the cluster. Something that gave the cluster extra mass, extra gravity, but gave off no light. He called this missing mass by a name in his native German. He called it dunkle Materie, dark matter. The term was born in that moment, in 1933, a quiet name for a profound unknown. Zwicky was not saying the matter was dark in the sense of being shadowy or sinister. He meant it quite literally. It did not emit light, it was dark, invisible, unseen. But it was there, he believed, and it had weight, and it pulled on the visible galaxies with its gravity. Zwicky's estimate of how much dark matter there was turned out to be larger than what we now believe. But the core of his insight was correct. There was more mass in the cluster than anyone could see. The visible stuff, the stars and gas, was only a fraction of the total. The rest was hidden, invisible, dark. This was a remarkable claim, and it did not sit easily with most astronomers of the time. The idea that most of the matter in the universe was something you could not see at all, something that gave off no light and seemed to interact with nothing except through gravity, was a very large pill to swallow. It was easier to assume that Zwicky had made a mistake. Maybe his speed measurements were off. Maybe there was ordinary matter in the cluster that he had missed, faint stars or diffuse gas that his instruments could not detect. Maybe the cluster was not really stable and was in the process of flying apart. There were many ways to set the problem aside, and for a long time, that is what happened. Zwicky's dark matter was noted, filed away, and largely left to sleep. Zwicky himself was a man ahead of his time in more ways than one. He was the first to propose that supernovas, the explosive deaths of massive stars, could leave behind a dense core made almost entirely of neutrons. He called them neutron stars. He also proposed that such explosions could produce cosmic rays, high-energy particles that rained down on Earth from space. He was a thinker who reached far, who grabbed hold of big ideas and shook them until they made sense. But the dark matter idea, his dunkle Materie, was perhaps the biggest of them all. And for nearly 4 decades it sat in the scientific literature like a seed waiting for rain. The field was not ready for it. The instruments were not sensitive enough. The evidence was not yet strong enough to force the conversation. So the universe kept its secret a while longer, and the galaxies kept spinning, and the coma cluster kept holding together against all reasonable expectation. It is worth pausing here to let the image of Zwicky settle. Picture him at his telescope, or at his desk covered in photographic plates and calculations. A man looking at numbers that refuse to cooperate. A man with the courage to say, aloud and in print, that most of the universe was invisible. He did not know what the dark matter was made of. He had no particle to point to, no theory to lean on. He had only the discrepancy, the gap between what he saw and what he knew should be true. And that gap, that not knowing, was enough for him. He named it, and he let it stand. There is a certain kind of patience in that, a willingness to live with a question mark rather than force an answer. Zwicky did not solve the dark matter problem. He opened it. He pointed to a door and said, "Something is behind this, even though we cannot see it." And then he moved on to other work, leaving the door ajar for others to find. Decades passed. The world went through a great war and came out the other side. Telescopes grew larger, instruments grew more sensitive, and the puzzle of the galaxy clusters did not go away. Other astronomers, studying other clusters, found the same problem. The visible mass was never enough. The galaxies always moved too fast. But the field as a whole still did not embrace the idea of dark matter. It was too strange, too uncomfortable. It is a pattern worth noticing. When the evidence points towards something deeply unfamiliar, the first response is often doubt. Not because the evidence is bad, but because the conclusion is so far from everyday experience. We are used to a world where what you see is what you get. A universe made mostly of invisible stuff is hard to accept. It takes time. It takes more than one man's measurements, more than one cluster's strange behavior. It takes a weight of evidence that cannot be set aside, and that weight was coming. Quietly, patiently, it was building. Vera Rubin was still a young woman when Zwicky first proposed dark matter, but her time would come, and when it did, the door Zwicky had opened would swing wide. For now, though, just hold the image of the coma cluster in your mind. A great gathering of galaxies, each one a vast island of billions of stars, all moving through the dark at speeds that should tear them apart. And yet they stay together. They have stayed together for billions of years. Something holds them, something with weight, something invisible. Zwicky saw this with the tools he had, nearly a century ago. He did his sums and he trusted them, and he gave the mystery its name, dark matter, the unseen weight of the universe. It is still unseen today. We have learned more about it, mapped its shape through other means, ruled out some possibilities and narrowed the field of others. But we have still not captured it directly. We have still not held a piece of it in our instruments the way we hold starlight or radio waves. In that sense, we are not so far from where Zwicky stood. We are still looking at a door he opened, still peering into the dark beyond it. Let your mind drift a little, if it wants to. Let the coma cluster hang in the dark behind your closed eyes. Hundreds of galaxies, each one made of hundreds of billions of stars, and around and between them, something else. Something that makes up most of the mass, something that does not shine. It is there now, as you breathe, as you rest. It was there in 1933, when Zwicky first wrote its name. It was there long before that, long before Earth formed, long before the sun ignited. It has been the quiet majority for most of cosmic history. And we, the small creatures who look up and wonder, have only just begun to notice it. The next step in the story belongs to another astronomer, working with another kind of observation in another decade. The shift from galaxy clusters to individual galaxies. The shift from a strange anomaly to a pattern that could not be ignored. But that is for the next part of the telling. For now, we sit with Zwicky, with his difficult personality and his far-reaching mind, with his German phrase, dunkle Materie, spoken into a scientific world that was not ready to hear it. With the coma cluster still holding together, still defying the simple sums of visible light. The mystery is patient. It does not demand to be solved tonight. It simply waits, as it has always waited, while we rest and breathe and slowly learn to see what has been there all along. The mystery waited, as it always does. For nearly 4 decades after Fritz Zwicky first wrote the words dunkle Materie, the idea of dark matter sat quietly in the scientific literature, noted but not pursued. A strange anomaly in a distant galaxy cluster, a problem that could perhaps be explained away by measurement errors or ordinary matter that was simply too faint to see. The field moved on. Other questions were asked and answered. Telescopes grew larger, photographic plates grew more sensitive, and the universe continued to spin through its long, slow rotations. But the seed Zwicky had planted was still there, resting in the dark soil of astronomy, waiting for the right conditions to grow. Those conditions arrived in the 1970s in the careful, persistent work of an astronomer named Vera Rubin. Vera Rubin was a woman who had to push her way into astronomy. The field was not always welcoming to her, and she had to carve out her own path, step by step, with quiet determination. She once told a story about being a young woman and writing to a university to ask for information about their graduate program, only to receive a reply suggesting she might be happier as a painter. She kept going anyway. She found her way to the study of galaxies, and by the 1970s, she was working at the Carnegie Institution in Washington, D.C., with a colleague named Kent Ford. Ford had built a sensitive instrument called a spectrometer, a device that could split light into its component wavelengths and measure very precisely how fast a distant object was moving. Together, Rubin and Ford decided to use this instrument to study something that seemed, on the surface, quite simple. They wanted to know how stars moved inside spiral galaxies. The question was straightforward. In a spiral galaxy, like our own Milky Way or the great galaxy in Andromeda, the visible matter is not spread out evenly. Most of the stars and gas are concentrated near the center in a bright, dense bulge. As you move outward from the center into the spiral arms and beyond, the starlight grows fainter and the visible matter grows thinner. This pattern is what you would expect. The center is bright and crowded. The outskirts are dim and sparse. If you were to guess how the stars orbit around the center of such a galaxy, you would use the same common sense that applies to the planets in our solar system. Mercury, close to the Sun, moves very fast in its orbit. Neptune, far from the Sun, moves much more slowly. The reason is that the Sun's gravity gets weaker with distance. Most of the mass in the solar system is concentrated in the Sun itself, right at the center. So the farther out you go, the weaker the gravitational pull, and the slower the orbital speeds. This relationship between distance and speed is what astronomers call a rotation curve. For our solar system, the rotation curve drops off sharply with distance. The inner planets zip around quickly. The outer planets drift along at a more leisurely pace. If a spiral galaxy were like the solar system, with most of its mass concentrated in the bright center, you would expect the same pattern. Stars near the center should orbit fast. Stars farther out, in the spiral arms and beyond, should orbit more slowly. The rotation curve should drop. This was the reasonable expectation. And when Rubin and Ford aimed their spectrometer at the Andromeda galaxy, the nearest large spiral to our own, they expected to measure a rotation curve that fell off with distance, a curve that matched the way the visible matter was distributed. The bright center, full of stars, should dominate the gravity. The dim outskirts should be gently coasting. What they found was something else entirely. The rotation curve did not drop. The stars far from the center were moving almost as fast as the stars near the center. Some were moving even faster. The speed stayed high, flat across the galaxy, right out to the farthest reaches they could measure. The stars in the outer parts of Andromeda were racing around the center at speeds that made no sense if the only gravity came from the visible stars and gas. According to the visible matter, those outer stars should have been flying off into intergalactic space. And yet they were not. They were held in their orbits, stable and calm, as if some unseen hand were adding extra gravity where the light was faintest. This was the same kind of problem Zwicky had seen in the Coma cluster, but now it was inside a single galaxy. The missing mass was not just a feature of giant clusters, it was right here, in the nearest spiral galaxy, in the very structure of a galaxy much like our own. Rubin and Ford did not stop with Andromeda. They measured other spiral galaxies, dozens of them, and in every case the pattern held. The rotation curves were flat. The outer stars moved too fast. The visible matter could not account for the gravity required to hold them. Whatever was providing the extra pull, it extended far beyond the visible disk of the galaxy. There seemed to be a large, invisible halo of mass surrounding each galaxy, a dark halo, providing the gravity that kept the outer stars in their swift orbits. Rubin was a careful scientist. She did not rush to announce a discovery. She checked and rechecked her measurements. She and Ford looked at galaxy after galaxy, and the flat rotation curves kept appearing. The evidence accumulated, quietly, patiently, until it could no longer be set aside. She presented her findings in a series of papers in the late 1970s. The response from the astronomical community was not immediate acceptance, but it was harder to dismiss than Zwicky's earlier work. Rubin's measurements were precise. They were repeated, they covered many galaxies, and they showed a clear, consistent pattern that demanded an explanation. The dark matter problem was no longer a single strange observation from a difficult Swiss astronomer in the 1930s. It was now a solid, replicated result, sitting at the heart of every spiral galaxy anyone bothered to measure. The invisible had become, in a strange way, ordinary. Think for a moment about what a flat rotation curve actually means. Picture a single star, far out in the disk of a spiral galaxy, orbiting the center. The visible matter, the bright stars and glowing gas, thins out around that star. According to the gravity of the visible matter alone, the star should be moving slowly, like Neptune drifting around the sun. But it is not moving slowly. It is racing along, held tight by a gravitational pull that comes from somewhere beyond the visible edge of the galaxy. The mass that provides that pull is not shining. It is not emitting any light at all. It extends in a vast, diffuse cloud around the galaxy, a halo of dark matter that outweighs the visible stars and gas by a large margin. The galaxy we see, the beautiful spiral with its arms and its bright center, is just the shining core of a much larger, darker structure. It is like a glowing ember at the heart of a great invisible fire. This image is worth holding for a moment. For decades, astronomers had studied spiral galaxies by looking at their light. They had mapped the stars, measured the gas, counted the clusters. They had built a picture of these galaxies based entirely on what they could see. And that picture, it now turned out, was incomplete. Not just slightly incomplete, fundamentally incomplete. The visible galaxy was only a small part of the whole. Most of the galaxy, most of its mass, was in a dark halo that extended far beyond the visible disk. The halo did not shine. It did not cast a shadow. It did not interact with light in any way. It simply exerted gravity. A lot of gravity. Enough gravity to dominate the rotation of the entire galaxy. Vera Rubin's work did something more than confirm Zwicky's old idea. It shifted the whole conversation. Before Rubin, dark matter was a curiosity, an oddity, a maybe. After Rubin, it was a serious problem that any complete theory of the universe had to address. The flat rotation curves were not subtle. They were dramatic. They told a clear story. Either our understanding of gravity was wrong at large scales, or there was a great deal of mass in the universe that we could not see. Most astronomers, faced with this choice, found the second option easier to accept, not because it was comfortable, but because it fit the data without overturning everything else we knew about physics. The idea of dark matter, strange as it was, preserved the known laws of gravity. It added a new ingredient to the universe, but it did not break the old recipes. And yet, the nature of that ingredient remained completely unknown. Rubin's rotation curves showed that dark matter existed, and they showed roughly where it had to be, in those vast halos around galaxies. But they could not say what the dark matter was made of. They could not give it a name, or a particle, or a place in the known families of matter. They only revealed the shape of its gravitational pull. The dark matter was like a hand in a dark room, gently pressing on the shoulder of every visible star. You could feel the pressure, you could measure the force, but you could not see the hand. Rubin herself was aware of the strangeness of what she had found. She did not claim to understand it. She simply presented the data and let it speak. She once said that in a spiral galaxy, the visible stars are like the tips of icebergs, and the dark matter is the great mass below the waterline. The metaphor had been used before, but in her hands it became precise. The visible galaxy was a thin frosting on a deep, dark cake. The frosting was what we had always studied. The cake was what actually mattered. As you lie here in the dark, you might think about our own galaxy, the Milky Way. It is a spiral galaxy, much like Andromeda. It has a bright center, spiral arms, a disk of stars and gas, and it has a dark matter halo, a vast, unseen cloud of mass that surrounds the entire galaxy and extends far beyond the visible edge. Right now, as you rest, the solar system is moving through that dark halo. The Earth is moving through it. Your body is moving through it. The dark matter particles, whatever they are, pass through you without a whisper. They do not bump into your atoms. They do not warm your skin. They are present, and they are weighty, and they are silent. The gravity they produce is enormous at the scale of the galaxy, but here, at the scale of your body, it is far too diffuse to feel. So you are held, gently, by something invisible. Something that keeps your galaxy together, something that has been here since the beginning. Rubin's legacy is not just a set of measurements. It is a shift in how we think about the cosmos. She showed us that what we see is not what we get. She made the invisible a subject of rigorous study. She brought dark matter in from the cold margins of astronomy and placed it at the center of the field. And she did it with care, with patience, with a quiet insistence that the data be taken seriously. She was not a loud voice. She was a steady one, and steady voices, in the end, carry further. Let the image of a flat rotation curve settle into your mind like a stone dropping into still water. A graph, if you were to draw it, with distance from the galaxy's center along the bottom and orbital speed along the side. For the solar system, that line drops. It falls away like a hillside sloping down to the sea. For a spiral galaxy, the line is flat. It runs straight and level, across the bright center, through the spiral arms, and out into the dark, empty-seeming spaces beyond. That flat line is a signature. It is the signature of dark matter. It is the mark of something unseen, pulling on the visible stars. It is a quiet fact, a piece of the universe's true shape, revealed not by light, but by motion, and it has been waiting for us to notice it all along. The story does not end here. Flat rotation curves are one line of evidence, one thread in a larger tapestry. There are other threads, other ways of seeing the unseen. The next thread comes from light itself and how it bends around invisible mass. It comes from a pair of galaxy clusters caught in the act of colliding, and a map of mass that sits apart from everything that shines. But that is for later. For now, we sit with Vera Rubin and her galaxies, with the flat lines on her graphs, with the quiet, steady voice that told the world, the universe is not what we thought it was. The dark halos are out there, surrounding every spiral galaxy, holding the outer stars in their swift orbits. And we, lying here in the dark, are inside one of them. The mystery is not far away. It is here. It is home. It simply waits, patient as always, while we drift a little further from the waking world. The mystery is patient. It waits in the dark halos around spiral galaxies, and it waits in the spaces between galaxies, and it waits in the way light travels across the universe. We have heard two lines of evidence so far. Fritz Zwicky, watching a cluster of galaxies move too fast to be held by the visible stars. Vera Rubin, watching stars within individual galaxies orbit too swiftly at their edges to be explained by the light she could measure. Both of these discoveries pointed toward the same conclusion. There is more mass in the universe than we can see. A lot more. But both of these discoveries relied on the same basic tool. They relied on measuring motion, watching how fast things move, and calculating how much gravity would be needed to hold them. Motion is a powerful clue, but it is not the only clue. There is another way to trace the presence of invisible mass, a way that does not depend on measuring speeds at all. It depends on light, and how light behaves when it passes near something heavy. Light, as a rule, travels in straight lines. A beam of light setting out across the universe will keep going in the same direction forever unless something makes it change course. This is the everyday experience of light. A flashlight pointed at a wall makes a straight beam. The sun's rays arrive in straight lines. Our eyes expect light to be direct. But the universe, as we have been learning, does not always follow everyday expectations. According to Albert Einstein's theory of general relativity, published in 1915, mass curves the space around it. A massive object, like a star or a galaxy or a cluster of galaxies, creates a kind of dip or curve in the fabric of space, and when light passes near that massive object, it follows the curve. The light is still traveling as straight as it can, but the space itself is bent, and so the light bends with it. The path of the light is deflected. This effect is called gravitational lensing. In plain terms, gravity acts like a lens, bending light around massive objects. Think of it this way. Imagine a stretched-out sheet of fabric, pulled tight and flat. If you roll a marble across it, the marble goes straight. Now imagine placing a heavy ball in the middle of the sheet. The fabric sinks down around the ball, creating a dip. If you roll a marble near that dip, the marble's path will curve. It is not that the marble changed its mind about where to go. It is that the surface it is rolling on has changed shape. Light behaves in a similar way. Space is the fabric. A massive object is the heavy ball, and light is the marble, following the curve of space as it passes by. This is not just a theory. It has been observed and measured many times. During a total solar eclipse in 1919, astronomers measured starlight bending around the sun exactly as Einstein had predicted. The effect is real, and it is precise. Gravitational lensing gives astronomers a tool. It lets them map where mass is, even if that mass gives off no light at all. They can look at the way light from distant background objects gets bent and distorted, and they can work backward to figure out how much mass must be present to create that bending. It is like seeing ripples on a pond and deducing where a stone must have fallen, even if you never saw the stone. The bending of light reveals the invisible hand of gravity, and this method, independent of any measurements of motion, has become one of the strongest pieces of evidence for dark matter. The clearest example of this method at work comes from a famous object in the sky called the bullet cluster. The bullet cluster is not a single galaxy cluster. It is two clusters that have collided. A long time ago, two large groups of galaxies crashed into each other, passing through one another in a slow, violent cosmic collision. The clusters themselves sit about 3.8 billion light-years away from us. The collision happened over hundreds of millions of years. When two galaxy clusters collide, the galaxies themselves are like tiny ships passing in a vast ocean. They mostly miss each other, because the space between galaxies in a cluster is very large. But the hot gas that fills the space between the galaxies does collide. The gas clouds slam into each other, heating up and slowing down. They produce X-rays that telescopes can detect. So after the collision, the hot gas ends up sitting in the middle, between the two groups of galaxies that have passed through each other. If all the mass in the cluster were made of ordinary matter, the mass and the hot gas would be in the same place. The gravity would follow the gas. The map of mass, traced by gravitational lensing, would overlap with the map of hot gas, traced by X-ray telescopes. But that is not what astronomers see when they look at the bullet cluster. They see something very different. The hot gas, the ordinary matter that crashed and slowed down, sits in the middle, but the map of mass, drawn by watching how light from background galaxies bends around the cluster, sits apart from the gas. The mass is concentrated around the two groups of galaxies that pass through each other, not around the gas that collided. This means that most of the mass in the cluster is not in the hot gas. It is not in the ordinary matter that slammed together. It is in something else, something that did not collide, something that passed straight through along with the galaxies. That something is dark matter. The bullet cluster provides a kind of picture of dark matter that is very hard to explain in any other way. The dark matter and the ordinary matter have been separated by the collision. The ordinary matter, the hot gas, got tangled up and left behind. The dark matter, whatever it is, moved on. It did not bump into anything. It did not slow down. It simply continued, carrying the galaxies with it through the force of its gravity. And now, after the collision, we can see the two components sitting apart. The glowing gas in the middle, the dark matter halos on either side. The light from distant background galaxies bends around those dark matter halos, tracing their shape, revealing their presence, even though the halos themselves give off no light. The mass is visible only through its effect on the path of light, and that mass is enormous. It outweighs the hot gas by a large margin. This is a powerful result because it does not rely on measuring how fast things move. It is a completely independent line of evidence. Zwicky measured speeds in galaxy clusters. Rubin measured speeds in individual galaxies. The bullet cluster shows us mass directly, through the bending of space itself, and all three lines of evidence point to the same conclusion. There is a large amount of mass in the universe that does not shine. It does not collide. It does not interact with ordinary matter in any way, except through gravity. It passes through gas clouds and through other dark matter halos, without slowing down, without heating up, without leaving a trace. It is transparent, not just to light, but to collisions. It is, in a very real sense, untouchable. Let the image of the bullet cluster sit in your mind for a while. Two great swarms of galaxies, each surrounded by a halo of dark matter, have passed through each other across millions of years of cosmic time. The galaxies sailed through, unscathed. The dark matter sailed through, unscathed. The hot gas, the ordinary matter, crashed and tangled and glowed with X-ray light. And now, if you could see the cluster through a telescope tuned to the bending of light, you would see the mass sitting in two large clumps on either side, with a glowing cloud of gas in between. It is like a cosmic photograph of a collision, frozen in time, the invisible made visible, not by its own light, but by its effect on the light of more distant things, the unseen, traced by the seen, the dark matter, usually so elusive, caught in the act of separating from ordinary matter. This kind of observation has been repeated for other colliding clusters. The pattern holds. Where clusters collide, the dark matter and the ordinary matter can be seen to separate. The lensing maps show mass where there is no gas. The X-ray maps show gas where there is less mass. The two components of the universe, dark and ordinary, behave differently because they are made of different things. Ordinary matter collides, heats up, slows down. Dark matter does none of these things. It simply moves through, silent and untroubled, holding its galaxies close. What does this tell us about the nature of dark matter? It tells us something quite specific. Dark matter does not interact with itself or with ordinary matter very much at all. If it did, the dark matter halos in the bullet cluster would have slowed down, just as the gas did. They would have tangled and heated. They did not. This makes dark matter very different from anything made of atoms. Atoms collide. Atoms interact. Dark matter, whatever it is, seems to interact almost entirely through gravity. It is a ghostly substance, present and weighty, but passing through everything else like a breeze through an open window. This is not just a vague idea. It is an observation, written in the bent light of distant galaxies. And so the evidence grows. Motion and light. Flat rotation curves in spiral galaxies, and bent light around colliding clusters. Each piece of evidence is different. Each uses a different method, a different instrument, a different set of physical laws, and yet they all converge on the same picture. The universe is full of mass that we cannot see. That mass outweighs the visible matter by roughly 5 or 6 times. It forms halos around galaxies. It binds clusters together, and when clusters collide, it moves through the wreckage without a scratch. This convergence of evidence is what makes dark matter such a sturdy idea in modern astronomy. It is not a single observation, it is not a single astronomer's pet theory. It is a web of observations, built up over decades, using different tools and different methods, all pointing toward the same conclusion. Zwicky saw it in the speeds of galaxies. Rubin saw it in the rotation of stars. Modern astronomers see it in the bending of light. The invisible leaves its fingerprints everywhere, if you know how to look for them. As you rest, you might imagine those fingerprints. Not literal fingerprints, of course, but traces. The curve of a graph, the arc of a bent beam of light, the map of mass sitting apart from a glowing cloud of gas. These are the signatures of dark matter. They are quiet signatures. They do not shout. They do not demand attention. They simply exist in the data, in the photographs, in the careful measurements that astronomers have gathered over nearly a century. The universe is speaking to us in a low, soft voice, telling us about the things we cannot see, and we, slowly, are learning to listen. The next question, of course, is what the dark matter actually is. We have established that it is there. We have mapped its shape in halos and clusters. We have watched it survive collisions. But we have not yet touched it. We have not identified a particle or a substance or a form. The search for what dark matter is made of is a story of its own, a story of deep underground laboratories and quiet detectors waiting for a single, rare event. But that is for later. For now, it is enough to sit with the bullet cluster. 2 clumps of dark matter holding their galaxies, having passed through each other like ghosts. And behind them, the bent light of background galaxies, tracing the shape of the invisible. The universe is strange, and it is calm, and it holds its secrets lightly, letting them be seen only by those who are patient enough to watch light bend slowly across the deep. The universe holds its secrets lightly, but it also allows us to narrow the field, to rule things out, to say, quietly and carefully, what a thing is not. This kind of work is less dramatic than discovering a new phenomenon. It does not make headlines, it does not win prizes, but it is essential. Ruling things out is a form of progress. Every wrong path we identify brings us closer to the right one, even if we do not yet know where the right one leads. So now, having traced the evidence for dark matter through the motions of galaxies and the bending of light, we can ask a quieter question. What could dark matter actually be? And just as importantly, what has it turned out not to be? When astronomers first began to take the dark matter problem seriously, they considered the simplest possible explanation. Perhaps the missing mass was just ordinary matter that was hard to see. Not exotic, not strange, just dim. The universe is full of things that do not shine brightly. There are clouds of cold gas that emit very little light. There are dust grains, fine as smoke, drifting between the stars. There are planets that wander through space without a parent star, dark and cold. There are dead stars, white dwarfs and neutron stars, that have burned through their fuel and now glow only faintly, cooling slowly across billions of years. There are even brown dwarfs, objects that are too small to ignite as stars, but too large to be called planets. They sit in a middle ground, radiating a faint trickle of heat and light, barely visible even to our best telescopes. All of these things are made of ordinary matter, the same protons, neutrons, and electrons that make up the Earth and the Sun and your own body. They are just dark, or nearly dark, in the visible part of the spectrum. Could the missing mass simply be a vast population of these dim, ordinary objects, scattered through the halos of galaxies? It was a reasonable question, and astronomers gave it a name, as astronomers do. They called this category of possible dark matter candidates by an acronym, MACOs. The letters stand for Massive Compact Halo Objects. Massive, because each object would need to have substantial mass. Compact, because they would be small enough to be faint or invisible. Halo, because they would need to sit in the dark outer halos of galaxies where the missing mass seemed to be. The name was a bit of a joke, a play on words that contrasted with another candidate we will meet later. But the search for machos was serious. How do you look for something that gives off almost no light? You cannot point a telescope at it and expect to see it directly. A cold, dark object drifting through the halo of the Milky Way is almost impossible to spot on its own. But there is a method. It relies on the same gravitational lensing we talked about earlier, but on a much smaller scale. When a massive object passes directly in front of a distant background star, the gravity of the foreground object bends the light of the background star, focusing it briefly. The background star appears to brighten for a short time, days or weeks, and then fades back to normal. This is called microlensing. The effect is tiny, and it requires very precise alignment, but it is real, and it has been measured many times. If the halo of our galaxy were full of machos, they would occasionally drift in front of distant stars in a nearby galaxy, like the Large Magellanic Cloud. The stars would wink brighter, briefly, and then settle back. By monitoring millions of stars over years, astronomers could count how often such brightening events occurred. From that count, they could estimate how many machos might be out there. In the 1990s and early 2000s, several large surveys did exactly this. Teams of astronomers watched the Large Magellanic Cloud and other nearby galaxies night after night, looking for the telltale brightening of a microlensing event. They found some events, but not nearly enough. The number of machos detected was far too small to account for the missing mass. Ordinary dim objects, the dead stars and wandering planets and cold gas clouds, could explain at most a few % of the dark matter. The vast majority of the missing mass had to be something else. The macho searches did not completely rule out every possible form of ordinary dark matter. There may still be some population of faint objects out there, but they ruled out the idea that the missing mass is made of the same stuff as stars and planets. Whatever dark matter is, it is not ordinary matter in a dim, hard-to-see form. It is something fundamentally different. This was an important result. It meant that the dark matter problem could not be solved by simply pointing more sensitive telescopes at the sky and looking harder. The dark matter was not hiding in the shadows. It was made of a different kind of stuff entirely. Something that does not interact with light at all, not because it is faint, but because it is not made of the particles that produce or absorb light. Ordinary matter, the stuff of atoms, interacts with light by its very nature. Electrons absorb and emit photons. That is how we see things. That is how telescopes work. If dark matter were made of atoms, even cold and dark ones, it would still leave some trace in the electromagnetic spectrum. It would block starlight or emit faint radio waves or glow in the infrared. But the dark matter halos appear to be truly dark, not dim, not faint, dark, transparent, invisible across every wavelength we have ever checked. This transparency is consistent with what we saw in the bullet cluster. The dark matter passed through the collision without slowing down. Ordinary matter, even in the form of diffuse gas, collides and heats up. Dark matter did not. It ghosted through. Machos made of ordinary matter would have collided, at least a little. The gas clouds certainly did. The fact that the dark matter separated cleanly from the gas tells us, again, that dark matter is not made of the same stuff as gas or stars or planets or people. So what is left? If dark matter is not ordinary matter, then it must be something else. Something that does not fit into the familiar table of particles that make up the visible world. Physicists began to think about what kind of particle could account for the observations. It would need to have mass, because it exerts gravity, a lot of gravity. It would need to be stable, or at least very long-lived, because the dark matter halos have been around for billions of years. It would need to interact very weakly with ordinary matter, if at all, because it leaves no trace in any telescope and passes through collisions undisturbed. And it would need to be abundant, making up about 5 or 6 times more mass than all the ordinary matter in the universe. This is a very specific set of requirements, and no known particle in the standard model of particle physics meets them all. The neutrinos, tiny ghostly particles that stream through the Earth in vast numbers, have some of the right properties. They are stable, they interact very weakly, but they are too light. Neutrinos move at nearly the speed of light, and they do not clump together under gravity, the way dark matter needs to clump to form galaxy halos. They are a form of hot dark matter, and the universe's structure requires cold dark matter, particles that move slowly enough to gather into clumps. Neutrinos cannot be the main ingredient, so the dark matter particle, if it exists, must be something new, something not yet discovered, something outside the standard model. This is a humbling thought. The standard model is one of the great achievements of modern physics. It describes every known particle and every known force except gravity. It has been tested to exquisite precision, and yet, if dark matter is a new particle, the standard model is incomplete. It describes only the 5%. It is a map of a small island in a vast ocean. The ocean itself remains uncharted. This is where the search stands now. Ruled out, ordinary dim matter. Ruled out, known particles like neutrinos as the main component. Left open, the possibility of a new kind of particle, something that has never been directly seen. The ruling out is not a failure. It is a clearing of the ground. It removes the easy answers, the comfortable answers, the answers that would have allowed us to keep our existing picture of matter intact. The universe is telling us, gently, that we need to expand that picture. There is more to matter than what we have found in our laboratories and our cosmic rays. There is something else, something that outweighs everything we know. As you lie here, half listening, half drifting, you might think about what it means to rule something out. Science is often pictured as a process of building up, adding new facts to a growing pile of knowledge. But a great deal of science is actually the opposite. It is a process of taking away, whittling down the possibilities, saying no, again and again, until only a few possibilities remain. Zwicky said yes to the idea of missing mass. Rubin said yes to the flat rotation curves. The lensing map said yes to dark matter halos. But then came the no. No, it is not ordinary gas. No, it is not dead stars. No, it is not wandering planets. No, it is not neutrinos. Each no is a step forward. Each no is a gift of clarity, carving away the underbrush so the true shape of the mystery can be seen. There is a kind of patience in this, too. The patience to accept that you do not yet know the answer, but you are getting closer by knowing what the answer is not. It is like sculpting. You start with a block of stone, and you remove piece after piece until the form emerges. The form of dark matter is still hidden in the stone, but the pieces we have removed, the ordinary matter and the hot neutrinos and the rest, those chips are on the floor. They are not wasted. They are the record of progress. The block is smaller now. The shape is beginning to suggest itself. The next step in the story is to talk about what that shape might be. The leading ideas for what the dark matter particle could actually be. The underground detectors, the quiet laboratories, the patient wait for a single particle to leave a trace. But that is for another section. For now, it is enough to sit with the ruled out, with the machos that turned out not to be there in sufficient numbers, with the ordinary matter that turned out to be only a small fraction of the whole, with the knowledge that whatever dark matter is, it is not like us. It is not made of atoms. It is not on the periodic table. It is something else, something new, something that has been waiting, patient as always, for us to finish ruling out the easy answers and start asking the harder ones. The dark matter does not mind being unknown. It has been unknown for the entire history of human thought. A little more time, while we narrow the field and sharpen our questions, will not trouble it at all. The easy answers have been ruled out. The dark matter is not dim stars, not cold gas, not wandering planets. It is not made of the same protons and neutrons and electrons that build the visible world. It is something else, something that does not fit into the familiar families of particles we have catalogued in our laboratories and our textbooks. And so the search moves inward, from the telescopes that watch the sky to the detectors that wait in the dark beneath the Earth. The search becomes a hunt for a new kind of particle. This is where the story leaves astronomy for a while and steps into the world of particle physics. These two fields, astronomy and particle physics, usually work at very different scales. Astronomy deals with the very large, galaxies, clusters, the vast filaments of the cosmic web. Particle physics deals with the very small, quarks, electrons, the fleeting fragments of smashed atoms. But dark matter sits at the intersection. It is a particle, or at least many physicists believe it is, but its effects are felt across cosmic distances. To understand it, we need to think about both scales at once. The very small particle that shapes the very large universe. The leading idea for what the dark matter particle might be goes by a name that sounds technical, but the idea behind it is fairly simple. Physicists call it a weakly interacting massive particle. The term is usually shortened to its initials, WIMP, but before we use that shorthand, let the full phrase sit for a moment. Weakly interacting. This means the particle does not feel the electromagnetic force. It does not absorb light or emit light. It does not bind into atoms. It passes through ordinary matter, almost as if the matter were not there. This is why dark matter halos do not collide or heat up. This is why the bullet cluster shows dark matter sailing through a cosmic crash without slowing down. The particles barely notice ordinary matter, and ordinary matter barely notices them. Massive. This means the particle has mass. It has weight, in the gravitational sense. Enough mass to pull on galaxies. Enough mass to shape the rotation curves that Vera Rubin measured. Enough mass to bend light around invisible clumps, as we saw with gravitational lensing. Particle. This means it is a discrete thing, a quantum of dark matter, just as an electron is a quantum of ordinary electric charge. A single unit of the invisible stuff. The WIMP idea emerged in the 1980s, not from astronomy, but from theoretical physics. Physicists working on extensions of the Standard Model, the great theory of known particles and forces, noticed that some of their mathematical frameworks predicted the existence of new particles with exactly the right properties to be dark matter. The particles would be stable, or nearly stable. They would interact only through the weak nuclear force and gravity. And if they were produced in the early universe, in the hot, dense moments after the Big Bang, their leftover abundance would match the amount of dark matter we measure today. This convergence is sometimes called the WIMP miracle, though the word miracle is perhaps too strong. It is more of a happy coincidence. The same calculations that describe how such a particle would behave also predict, roughly, how much of it should still be around. And the prediction lines up, within the broad uncertainties, with the dark matter density we infer from astronomical observations. This alignment is part of why the WIMP idea has been taken seriously for decades. It is not just a guess, it is a prediction that emerges naturally from certain well-motivated theories. But a prediction is only a prediction. To know if WIMPs are real, we need to detect them directly. We need to catch one in the act of interacting, however faintly, with ordinary matter. And this is a very difficult thing to do. If WIMPs exist, billions of them are passing through your body every second. They stream through the Earth as if it were empty space. The weak interaction is called weak for a reason. The chance that any single WIMP will bump into an atomic nucleus is vanishingly small. So to have any hope of spotting one, physicists need to build detectors that are both very large and very quiet. They need a lot of material for the WIMPs to pass through, to increase the odds of a rare collision, and they need to shield that material from every other kind of particle that might create a false signal. Cosmic rays from space rain down on the Earth's surface constantly. Radioactive elements in the surrounding rock emit particles. Even the materials of the detector itself can produce tiny flashes of energy that mimic a dark matter signal. To escape all this noise, the detectors go underground. Deep underground. Around the world, in old mines and beneath mountains, There are laboratories carved into the rock. The Gran Sasso Laboratory in Italy sits under nearly a mile of dolomite rock. The Sanford Underground Research Facility in South Dakota occupies a former gold mine. The Snow Lab in Canada is built into a working nickel mine more than a mile beneath the surface. There are others. In China, in the United Kingdom, in South Korea. These are quiet places. The rock above them filters out the cosmic rays, the constant rain of protons and heavier nuclei from space. The walls are lined with shielding materials, layers of lead and copper and water, to block the natural radioactivity of the surrounding stone. The detectors themselves are made of carefully selected materials, purified to remove every trace of radioactive isotopes. The goal is to create the quietest place on Earth, a place where almost nothing happens, a place where the only thing that might disturb the stillness is a single dark matter particle, wandering through after a journey of billions of years, and choosing that moment, that detector, that atom, to touch. What does a dark matter detector actually look like? Many of the WIMP detectors are built around a simple idea: a tank of liquid xenon or a crystal of germanium or silicon cooled to very low temperatures. The liquid or crystal is the target. If a WIMP passes through and strikes a nucleus, the nucleus recoils. It moves, just a tiny bit. That movement produces a faint flash of light, or a tiny amount of electric charge, or a small rise in temperature. The detector is surrounded by sensors that watch for these signals. The flash is faint, the charge is tiny, the temperature rise is minuscule, measured in millionths of a degree, but the instruments are sensitive enough to see it. The hard part is not seeing the signal. The hard part is knowing whether the signal came from a WIMP or from something else. Even deep underground, there are background events, neutrons from the surrounding rock, traces of radioactive elements in the detector itself, neutrinos from the sun streaming through in their trillions every second. The art of direct detection is the art of discrimination, telling the dark matter signal apart from the noise. For decades now, these detectors have been running. They have grown larger and more sensitive with each generation. The early experiments were tabletop-sized. The current generation uses tons of liquid xenon. The next generation will use tens of tons. The searches have pushed deeper and deeper into the parameter space, the range of possible WIMP masses and interaction strengths. And as of now, no WIMP has ever been directly detected. The detectors have seen nothing that cannot be explained by known backgrounds. The null result is clear and consistent. This does not mean WIMPs do not exist. It means that if they do exist, they interact even more weakly than some of the simplest models predicted. The parameter space is narrowing. The WIMP is being squeezed. But it is not ruled out, not yet. There is another candidate that many physicists take seriously. A different kind of particle, much lighter than a WIMP. It is called the axion. The axion was first proposed in the 1970s to solve a different problem in particle physics, a puzzle about why the strong nuclear force behaves in a certain symmetric way. The axion, if it exists, would be extraordinarily light, trillions of times lighter than an electron. It would interact even more feebly than a WIMP, but it could still be the dark matter because it could be produced in enormous numbers in the early universe, forming a cold, diffuse sea of particles that fills the galaxy. Axion searches use a different method. They look for axions converting into photons, particles of light, in the presence of a strong magnetic field. The experiments are called haloscopes, and they are essentially very sensitive radio receivers, tuned to listen for a faint signal at a frequency that depends on the axion mass. The frequency is unknown, so the experiments must scan, slowly and patiently, across a wide range. The axion, like the WIMP, has not been found. The search continues. It is important to say plainly that we do not know what the dark matter particle is. Not yet. The WIMP and the axion are the leading ideas, but they are not the only ones. There are other proposals. Sterile neutrinos, heavy versions of the familiar neutrino that would interact even more weakly. primordial black holes formed in the early universe that could make up some or all of the dark matter. Some physicists have explored the idea that our understanding of gravity itself might need modification, though this approach has grown more difficult to sustain as the evidence from lensing and the bullet cluster has accumulated. The field is open, the question is unsettled, and that is fine. That is how science works. The not knowing is not a failure. It is the condition of the search. Think for a moment about what it means to build a detector for something you have never seen, to carve a cavern out of deep rock, to fill it with ultra-pure liquid, to cool it to temperatures colder than the space between stars, and to sit, for years, waiting for a single atom to twitch. The patience required is enormous. The experimenters know that they may see nothing. They know that a null result is still a result, still a narrowing of the field, still a step forward. But they also know that the discovery, if it ever comes, will be quiet. A handful of events, a small excess above the expected background, a signal that builds slowly, over months and years, until it cannot be explained away. There will be no flash of light in the sky, no dramatic moment, just a graph, with a small bump and a long, careful process of checking and rechecking until the world is convinced. The discovery of dark matter, if it happens, will be a whisper, not a shout. As you lie here, you might picture one of those underground laboratories, a cavern in the dark, far below the surface of the earth. The rock above presses down with the weight of a mile of stone. The air is cool and still. The detector sits in its shielding, a cylinder of steel and copper and lead, with the liquid xenon inside, quiet and cold. The scientists are not there. The lab is automated. The data streams to computers on the surface, where it is analyzed and checked, but the detector itself sits in the stillness, waiting. It has been waiting for years. It may wait for many more. And if a dark matter particle, one of the countless billions streaming through the Earth, happens to strike a xenon nucleus, the detector will register a tiny flash, a brief, faint signal in the quiet. A moment of contact between the visible world and the invisible. That moment may have already happened, buried in the data, waiting to be teased out, or it may happen tomorrow, or it may never happen if dark matter turns out to be something other than a WIMP. The waiting is the work, the patience is the practice. The search for dark matter particles is one of the great quiet quests of our time. It does not make headlines often. It does not produce images of the kind that fill astronomy books, but it is the necessary next step. Zwicky saw the missing mass. Rubin mapped its shape. The lensing observations confirmed its presence. The particle physicists now must find its nature, and they are doing so with the tools they have, in the quietest places they can make, waiting for the faintest of touches. The dark matter does not mind being searched for. It has been passing through the Earth for billions of years, indifferent to the planet and the life on it. A few more decades of quiet waiting in a cavern beneath the mountains will not trouble it at all. The search for the dark matter particle continues in its quiet way, deep beneath the mountains, in tanks of liquid xenon, and in the hum of radio receivers tuned to frequencies no one has yet named. But while the particle physicists wait for a single atom to twitch, there is another way to think about dark matter. Not as a particle, not as a thing to be caught, but as a force that shaped the entire visible universe. A scaffold, a skeleton, an invisible architecture upon which everything we see was built. To understand this, we need to step back in time, not just decades to Zwicky and Rubin, but billions of years, all the way back to the early universe, a few 100,000 years after the Big Bang. At that time, the universe was a hot, dense soup of particles and light. Ordinary matter, the protons and electrons that would later form atoms, was spread through space like a thick fog. The fog was not perfectly smooth. There were tiny ripples, small variations in density from place to place. Some regions were very slightly denser than average, some were very slightly thinner. These ripples were minuscule, variations of perhaps 1 part in 100,000, but they were there. We know this because we can still see them today, frozen into the faint afterglow of the early universe, the cosmic microwave background, which we will talk more about later. Those tiny ripples were the seeds of everything that would come later, the seeds of galaxies, the seeds of clusters, the seeds of the great cosmic structures we see around us now. Gravity is a patient sculptor. Over time, it pulls matter toward denser regions. A slightly denser patch of the early universe has slightly more gravity than its surroundings. It pulls in more matter. That makes it denser still. The process feeds on itself. Given enough time, the tiny ripples grow into large clumps. The clumps become galaxies. The galaxies gather into clusters. The clusters align along vast filaments, forming a web-like structure that spans the observable universe. This is the story of cosmic structure formation. It is a story that took billions of years to unfold, and it is still unfolding now, in the slow drift of galaxies toward each other, in the quiet merging of clusters in the deep. But there is a problem with this story, a problem we have already met in a different form. The problem is time. The universe is about 13.8 billion years old. That is a long time by human standards, but it is not a very long time by cosmic standards. Gravity is a weak force. The tiny ripples in the early universe were very small. If the only matter in the universe were ordinary matter, the protons and electrons and atoms that make up the visible world, then gravity would not have had enough time to build the structures we see today. The ripples would have grown too slowly. By the present day, the universe would be a much smoother, duller place. There would be no large galaxies, no clusters, no cosmic web, just a thin, even distribution of gas, slowly cooling, never clumping. This is where computer simulations come in. Astronomers can model the history of the universe inside a computer. They start with the conditions of the early universe, the tiny ripples measured in the cosmic microwave background. They add the known laws of physics, gravity, gas dynamics, the expansion of space, and they let the simulation run, ticking forward through billions of years of virtual time to see what kind of universe emerges. When they run these simulations with only ordinary matter, the result does not look like the real universe. The galaxies are too small. The clusters are too few. The structure is too weak. The simulation fails. But when they add dark matter to the simulation, everything changes. The dark matter does not interact with light. It does not feel pressure from radiation, so it can start clumping earlier than ordinary matter. Long before atoms formed, long before the cosmic microwave background was released, the dark matter was already gathering. The tiny ripples in the dark matter began to grow as soon as the universe became matter-dominated. By the time ordinary matter was free to collapse, the dark matter had already built a framework, a scaffolding of clumps and filaments, invisible but gravitationally powerful. The ordinary matter fell into this scaffolding. It slid down the gravitational wells that the dark matter had prepared. It collected in the densest regions, cooled and formed stars. The galaxies we see are not just random accumulations of stars. They are the bright cores of much larger dark matter structures. The visible universe is the glittering surface of an invisible edifice. This is a profound shift in perspective. For most of human history, we thought the universe was built from the things we could see. The stars were the fundamental objects, and the space between them was empty. Now we understand that the visible stars and galaxies are more like foam on a wave. The wave itself, the driving structure beneath, is dark matter. The dark matter halos that Vera Rubin inferred from her flat rotation curves are not just passive cocoons. They are the original structures. They formed first. The galaxies followed. In this sense, dark matter is not an extra ingredient added to a universe of ordinary matter. It is the primary ingredient. The ordinary matter is the extra, the frosting on a dark cake that fills the cosmos. The idea of a cosmic scaffolding leads naturally to the image of a cosmic web. The web is the largest scale structure in the universe. It is a pattern of filaments and clumps, like a three-dimensional spider's web stretched across billions of light years. The filaments are made mostly of dark matter. They are the threads of the scaffold. Where the filaments intersect, the dark matter is densest. These intersections are where galaxy clusters form. The clusters are the nodes of the web, the knots where the threads meet. Between the filaments, there are vast empty regions called voids. These are not completely empty, but they contain far fewer galaxies, far less ordinary matter, and far less dark matter. The voids are the spaces between the threads. The cosmic web is not a metaphor, it is a real structure. Astronomers have mapped it by surveying the positions of millions of galaxies. The galaxies trace the filaments like lights on a dark highway. The highway itself, the underlying dark matter structure, is invisible, but the galaxies reveal its shape. Think about this for a moment. The largest thing we know of, the cosmic web, is mostly invisible. The threads that connect the galaxies across billions of light years are made of something we cannot see. We infer their existence from the galaxies that ride along them, like dew on a spider's web in the morning. The web is there. It has been there since the first few 100 million years of the universe's history. It was built by dark matter, patiently clumping under the force of its own gravity, while ordinary matter was still too hot and too tangled with radiation to follow. And when ordinary matter finally cooled and became free, it found a ready-made landscape of gravitational hills and valleys. It poured into the valleys. It lit up with the first stars, and the universe as we know it began. This story, the story of structure formation, is one of the strongest arguments for dark matter. It does not rely on measuring speeds or bending light. It relies on the simple fact that the universe we see exists in the form it does. Galaxies are too big and too clustered to have formed from ordinary matter alone in the time available. Dark matter solves this problem neatly. It provides the extra gravity needed to speed up the clumping. It acts as the seed. Without it, the cosmic web would not exist. Without it, the Milky Way would not exist. Without it, we would not be here to wonder about it. The computer simulations that demonstrate this are some of the most complex calculations ever performed. They track the gravitational interactions of billions of particles across cosmic time. They model the behavior of gas, the formation of stars, the feedback from exploding supernovas and growing black holes. The simulations have names like Illustris, Eagle, and Millennium. They run on supercomputers, sometimes for months, processing numbers at a scale that is hard to comprehend. And when they finish, the simulated universes look remarkably like the real one. The galaxies have the right sizes and shapes. They group into clusters of the right sizes and numbers. They trace out a cosmic web that matches the one we observe. But they only work if dark matter is included. If you turn off the dark matter, the simulated universe looks wrong, flat, featureless, unrecognizable. This does not prove that dark matter is a particle. The simulations assume dark matter is made of particles that interact only through gravity. If dark matter turned out to be something else, something that modified gravity rather than adding mass, the simulations would need to be rethought. But so far, the particle dark matter model has been remarkably successful at reproducing the large-scale structure of the universe. The cosmic web, in the standard picture, is a dark matter web. The galaxies are just along for the ride. Let the image of the cosmic web settle into your mind. A vast, three-dimensional net spanning the observable universe. Filaments of dark matter stretching across hundreds of millions of light years. At the intersections, great clusters of galaxies, the largest bound structures in existence. In the voids, silence and near emptiness, vast bubbles of space where very little happens. The whole thing is growing, slowly, even now. Gravity is still pulling dark matter into the filaments. The filaments are growing denser. The voids are growing emptier. The web is tightening almost imperceptibly across billions of years. It is a living structure, in a slow, gravitational sense, and we are inside it. Our galaxy sits on a filament, in a small group of galaxies, near the edge of a larger cluster. We are a speck on a thread in a web that stretches beyond our ability to picture, and the web itself is made of something we cannot see. This is a comforting thought in its way. It means that the visible universe, the stars and planets and glowing nebulas, is not adrift in emptiness. It is anchored, it is held. It is part of a larger structure, even if that structure is invisible. The dark matter that holds individual galaxies together also connects those galaxies across vast distances. It is the glue that binds the cosmos. Without it, everything would fly apart, or more likely, would never have come together in the first place. The universe would be a cold, diffuse place, without complexity, without structure, without life. In a very real sense, we owe our existence to dark matter. The invisible made the visible possible. The next part of the story takes a different turn. We have been talking about dark matter, the unseen mass that pulls things together. But there is another unseen component of the universe, something even stranger, something that pushes things apart. The dark energy, the force that is speeding up the expansion of the universe. To get there, we need to take a quiet step back and think about the expansion itself, how it was discovered, what it means, and how astronomers came to realize that the expansion is not slowing down as everyone expected. That is for another section. For now, we sit with the cosmic web, with the dark scaffolding that underlies everything we see, with the knowledge that the galaxies are not isolated islands, but connected nodes in an invisible network. And that network, the great dark web, is the true structure of the universe. It is quiet, it is patient, it has been growing for 13.8 billion years. And it will continue to grow, long after our own galaxy has faded, long after the stars have burned out, long after the last light in the visible universe has gone dark. The dark matter will still be there, holding its shape, waiting for whatever comes next. We have spent a long time with dark matter, with the unseen mass that holds galaxies together and weaves the cosmic web, with Zwicky's cluster and Rubin's rotation curves and the bent light around colliding clusters, with the quiet search for a new particle in caverns deep beneath the mountains. Dark matter pulls things together. It is the great gatherer, the sculptor of structure, the invisible hand that clumps and clusters and builds. But there is another invisible component of the universe, and it does the opposite. It pushes things apart. To understand it, we need to step back from the structures dark matter built and think about the stage those structures sit on. The stage itself is not static. It is growing. The universe is expanding, and that expansion, it turns out, has a story of its own. The idea that the universe is expanding is now a settled part of our picture of the cosmos, but it was not always so. For a long time, the default assumption among astronomers was that the universe was static, eternal and unchanging. The stars moved, the planets orbited, but the overall framework of space was fixed. This was not a scientific conclusion so much as a habit of thought. The night sky looks the same night after night, century after century. The constellations hold their shapes. The Milky Way arches across the darkness as it always has. It is natural to assume that the universe at large is a stable, steady thing. But assumptions, even natural ones, can be wrong. The first strong evidence that the universe is not static came from the work of an American astronomer named Edwin Hubble, and from others who laid the groundwork before him. In the early decades of the 20th century, astronomers were studying the light from distant galaxies. They used a tool called a spectrograph, which splits light into its component wavelengths, spreading it out into a rainbow of colors. When you look at the spectrum of a star or a galaxy, you see not just a smooth rainbow, but a pattern of dark and bright lines. These lines are like fingerprints. They correspond to specific elements like hydrogen and helium and calcium, absorbing or emitting light at specific wavelengths. By studying these spectral lines, astronomers can learn what a distant object is made of, and also how fast it is moving relative to us. The key to measuring motion lies in something called the Doppler shift, but the simpler term is redshift. When a light source moves away from you, its light waves get stretched. The stretching shifts the light toward the red end of the spectrum, where the wavelengths are longer. When a light source moves toward you, its light waves get compressed. That shifts the light toward the blue end of the spectrum, where the wavelengths are shorter. This is the same effect that makes a siren sound higher as it approaches and lower as it recedes, only with light instead of sound. By measuring how much the spectral lines of a galaxy are shifted toward the red or the blue, astronomers can calculate how fast that galaxy is moving away from us or toward us. When astronomers began measuring the redshifts of distant galaxies in the early 20th century, they found something striking. Most galaxies are redshifted. They are moving away from us. This was not entirely a surprise. A few galaxies had already shown redshifts, but the pattern, as more and more galaxies were measured, became clear. The farther away a galaxy is, the faster it is moving away. This relationship is now called the Hubble law, after Edwin Hubble, who published a key paper on it in 1929. The universe is expanding. The space between galaxies is stretching. It is not that galaxies are flying through space like shrapnel from an explosion. It is that space itself is growing, carrying the galaxies along with it. The common metaphor is a loaf of raisin bread rising in the oven. The dough expands, and the raisins move apart from each other, even though they are not moving through the dough. Each raisin sees every other raisin receding, and the farther away a raisin is, the faster it seems to move, because there is more expanding dough between them. This was a profound shift in thinking. The universe was not static. It had a history. If space was expanding now, then in the past, it must have been smaller. Extrapolate backward far enough, and you reach a point where everything was squeezed into an extraordinarily hot, dense state. This is the basis of the Big Bang theory. The expansion of the universe was the first clue that the cosmos has a story, a beginning, a progression through time. It is not eternal and unchanging. It is dynamic. It moves. It grows. For most of the 20th century, after the expansion was established, astronomers assumed that the expansion must be slowing down. This was a reasonable assumption, grounded in the known laws of physics. Gravity pulls things together. The matter in the universe, all the galaxies and gas and dark matter, exerts a collective gravitational pull on the fabric of space itself. That pull should act as a brake on the expansion. The universe should be expanding more slowly now than it did in the past. The question, astronomers thought, was not whether the expansion was slowing, but by how much. Would the expansion slow enough to eventually stop and reverse, leading to a big crunch, or would it slow but never quite stop, leading to an eternal, gradual coasting into darkness? The fate of the universe seemed to hang on the deceleration rate. The search was on to measure it. To measure the deceleration, astronomers needed a way to gauge distances very precisely across vast cosmic spans. They needed a standard candle, an object whose true brightness is known, so that its apparent dimness can be used to calculate its distance. Think of a row of identical light bulbs stretching into the fog. The farther away a bulb is, the dimmer it looks. If you know how bright each bulb truly is, you can judge its distance by how dim it appears. In astronomy, finding reliable standard candles is difficult. Most celestial objects vary in their true brightness. What looks dim might be a bright object far away, or a faint object nearby. To untangle this, you need a class of objects whose true brightness is consistent from one example to the next. By the 1990s, astronomers had identified a promising candidate, a particular kind of exploding star, called a Type Ia supernova. These supernovas occur when a white dwarf star, the dense remnant of a sun-like star, pulls matter from a companion star until it reaches a critical mass. At that point, a runaway nuclear reaction ignites, and the white dwarf explodes. Because the trigger mass is always the same, the explosion is always roughly the same brightness. A Type Ia supernova in a distant galaxy shines with a predictable luminosity. It is a standard candle. By measuring how bright it appears in our telescopes, astronomers can calculate how far away it is. And by measuring its redshift, they can calculate how fast its host galaxy is moving away from us. Combining these two measurements gives you a history of the expansion of the universe. You can look back across billions of years and see how the expansion rate has changed. Two independent teams set out to do exactly this in the late 1990s. The Supernova Cosmology project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. They were competing, in the friendly and driven way that scientific teams often do, to be the first to map the expansion history of the universe using distant Type 1a supernovas. They expected to measure the deceleration. They expected to find that the expansion was slowing down. That was the reasonable expectation. That was what gravity demanded. What they found was something else entirely. The distant supernovas were dimmer than they should have been. Not just a little dimmer, significantly dimmer. If the expansion had been slowing down as expected, the supernovas would have been brighter, because a slowing expansion puts the distant universe at a somewhat different distance scale. The dimness meant the supernovas were farther away than the standard slowing down model predicted. And that meant the expansion of the universe was not slowing down at all. It was speeding up. The expansion is accelerating. Some force is pushing space apart, overcoming the gravitational pull of all the matter in the universe, driving galaxies away from each other at an ever-increasing rate. This result was so unexpected that both teams spent months checking their data, looking for errors, ruling out alternative explanations. Could the supernovas be dimmed by dust? Could they be different in the early universe? Could the measurements be wrong? They checked and rechecked. The result held. In 1998, both teams published their findings. The universe is accelerating. The discovery was honored with the Nobel Prize in Physics in 2011, shared by Perlmutter, Schmidt, and Rees. It was a turning point in cosmology, as significant as Hubble's discovery of the expansion itself. What causes the acceleration? No one knows. The name given to the unknown force is dark energy. Like dark matter, the word dark here does not mean sinister. It means unknown, unseen, not directly detected. Dark energy is a label for a mystery. It is the name we give to whatever is pushing the universe apart. And like dark matter, it appears to be the dominant component of the cosmos. But we are getting ahead of ourselves. Before we talk about what dark energy might be, before we name the ideas and the uncertainties, we should simply sit for a moment with the fact of the acceleration. The universe, which has been expanding since its earliest moments, is not coasting gently to a stop. It is speeding up. The space between galaxies is stretching faster now than it did billions of years ago, and we do not know why. Let that sit. The dark matter we talked about earlier pulls things together. It builds structure. It forms the cosmic web. And now we learn of something else, something that pushes things apart. These two invisible components, dark matter and dark energy, are in a kind of tension. Dark matter clumps. Dark energy smooths. Dark matter gathers. Dark energy scatters. They are opposite tendencies, both unseen, both dominant, and both mysterious. The universe is shaped by the interplay of two invisible forces, one pulling in, one pushing out. And we, the small observers on a small planet, have only just begun to notice them. The story of dark energy is in some ways even stranger than the story of dark matter. Dark matter, at least, is a thing, a substance, a particle perhaps, that we might one day catch in a deep underground detector. Dark energy is not obviously a particle at all. It seems to be a property of space itself, an energy that lives in the vacuum, a steady hum of repulsion that grows as space grows. But that is for later. For now, it is enough to know that the expansion is speeding up, that the discovery was made not by looking at what was there, but by looking at what was unexpectedly dim. The supernovas, those brief, bright explosions in distant galaxies, told us that the universe is not behaving as we thought it should. They whispered, across billions of light years, that something else is out there, something that pushes, something that we still cannot name. As you lie here, you might imagine the expansion, not as an explosion, but as a slow stretching. The space between you and the pillow beneath your head is expanding, though far too slowly to measure, held tight by the gravity of the Earth and the forces that bind ordinary matter. But out in the deep voids between galaxy clusters, where gravity is weak, the expansion is winning, The voids are growing. The filaments of the cosmic web are being stretched. The universe is becoming emptier, darker, more spread out, with every passing billion years, and the rate of that stretching is increasing. The push is getting stronger relative to the pull. Dark energy, whatever it is the dominant force in the universe today, and we have only known about it for a little over 2 decades. The mystery is fresh, the not knowing is recent, and it waits, patient as ever, for us to understand. The mystery is fresh, and it waits. The expansion of the universe, first detected in the redshifts of distant galaxies, had been known for most of the 20th century, and for most of that time, astronomers assumed the expansion was slowing down. It was a reasonable assumption. Gravity pulls. Mass tugs on mass. A universe full of galaxies and gas and dark matter should be pulling on itself, gradually breaking the outward rush set in motion by the Big Bang. The only question was how much braking was happening. Would the expansion slow to a halt and reverse? Would it slow but never quite stop? The answer, it turned out, was neither. The expansion is not slowing, it is speeding up. And the way we found that out is a story worth telling slowly, in the quiet of the night. The story centers on a particular kind of exploding star. We touched on it briefly before, but now we can take our time with it. The star is called a Type 1a supernova. Let the name sit for a moment. It is a label, nothing more. What matters is not the name, but what these stars do. A Type 1a supernova is the death of a white dwarf. A white dwarf is the leftover core of a star that was not massive enough to explode on its own. When a star like our Sun runs out of fuel, it sheds its outer layers and leaves behind a dense, hot core. That core is a white dwarf. It is small, about the size of the Earth, but it contains roughly the mass of the Sun. It is held up not by the heat of nuclear fusion, like a living star, but by a quantum mechanical pressure called electron degeneracy. In simple terms, the electrons in the white dwarf resist being squeezed any further. The star is stable. It can sit that way for billions of years, slowly cooling. But if a white dwarf has a companion star nearby, something different can happen. The white dwarf's gravity can pull gas from the companion. Over time, material builds up on the surface of the white dwarf. The mass grows. When the mass approaches a particular limit, about 1.4 times the mass of our Sun, the pressure and temperature in the core reach a point where carbon atoms begin to fuse. This is the critical moment. The fusion ignites, and unlike in a normal star, the white dwarf cannot expand to regulate the reaction. The entire star undergoes a runaway thermonuclear explosion. It is destroyed completely, in a blast that briefly outshines its entire host galaxy. Because the explosion happens at nearly the same mass limit every time, the brightness of the explosion is nearly the same every time. The physics of the detonation is consistent, the amount of fuel is consistent, the energy released is consistent. This is what makes Type 1a supernovas so valuable. They are standard candles. A standard candle is any object whose true brightness, what astronomers call its intrinsic luminosity, is known. If you know how bright something truly is, you can measure how bright it appears in your telescope, and from the difference, you can calculate how far away it is. The dimmer it looks, the farther away it must be. It is a simple principle, the same one your eyes use to judge distance every day. A car's headlights look dimmer when the car is far away. A Type 1a supernova looks dimmer when it explodes in a galaxy billions of light-years distant. But using this principle in practice is not simple. The universe is not a clean, empty space. There is dust between galaxies that can dim the light, making a supernova look farther away than it truly is. There are variations among Type 1a supernovas themselves. They are not perfectly identical. Some are slightly brighter, some slightly fainter. Astronomers have learned to correct for these differences. They have studied the light curves, the way the brightness rises and falls over weeks and months. They have found correlations between the shape of the light curve and the peak brightness. A supernova that brightens and fades more slowly tends to be intrinsically brighter, By measuring the light curve carefully, astronomers can standardize the candles, adjusting for these small differences to get a more precise distance. The work is painstaking. It requires patience and careful calibration. But by the 1990s, the techniques were mature enough to attempt something ambitious: measure the expansion history of the universe. Two teams took up the challenge. One was the Supernova Cosmology project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory. The other was the High Z Supernova Search Team, led by Brian Schmidt at the Mount Stromlo and Siding Spring Observatories in Australia, with Adam Rees playing a key role in the analysis. The two teams were rivals, pushing each other to go deeper, to find more supernovas, to refine their methods. Their goal was the same: find a large sample of distant Type 1a supernovas, measure their distances and their redshifts, and plot them on a graph. The graph would show how the expansion rate has changed over cosmic time. The slope of the line would tell them the deceleration rate. They expected to measure how much the expansion was slowing. Finding distant supernovas is not easy. A supernova is a brief event. It flares up over a few weeks, shines at peak brightness for a short time, and then fades over months. To catch one, you need to take images of the same patch of sky repeatedly and look for new points of light that were not there before. The teams developed clever strategies. They would take deep images of the sky just after a new moon, when the sky is darkest. Then they would take images of the same fields a few weeks later, before the moon grew bright again. By subtracting the two images, they could pick out new objects. A new dot of light, not present in the earlier image, could be a supernova. Then they had to act quickly. They needed to get spectra, to confirm the supernova type and measure its redshift, before it faded. They needed to track the light curve as it declined. This required telescope time on some of the largest instruments in the world, scheduled in advance with tight coordination. The work took years, hundreds of nights of observing, thousands of images, careful screening to separate the Type 1a supernovas from other kinds of exploding stars and active galaxies. Slowly, the samples grew. Perlmutter's team published results through the mid-1990s. Schmidt and Rees's team began publishing a few years later. By 1998, both teams had enough data to draw conclusions. The conclusions were not what anyone expected. The distant supernovas were too dim. A supernova at a given redshift, a given speed of recession, appeared fainter than it should if the expansion had been slowing down. Fainter means farther away. Farther away means the light has traveled across more space to reach us. More space means the expansion has been doing something unexpected. If the expansion had been slowing down, the universe would have been expanding faster in the past, and the distance to a given redshift would be smaller. A slowing expansion puts a distant galaxy at a somewhat closer distance for its redshift. But the supernovas were farther. The expansion had been slower in the past. It was speeding up now. Both teams reached the same conclusion independently. The expansion of the universe is accelerating. The deceleration parameter they had set out to measure turned out to be negative. Instead of a brake, there was an accelerator. The result was so surprising that both teams spent months checking for errors. Could dust be making the supernovas look dimmer? Dust does dim light, but it also reddens it, and the supernovas did not show the color changes that dust would produce. Could the supernovas themselves be different in the distant past? The teams checked every known correlation, every possible evolution effect. The data held. Could there be some other systematic error, some subtle bias in the way the supernovas were selected or measured? Both teams, using different telescopes, different search strategies, different analysis methods, got the same answer. The acceleration was real. In early 1998, the High Z team published their results. Later that year, the Supernova Cosmology project published theirs. The papers were landmark events in cosmology. They changed the field. Within a few years, the acceleration was confirmed by other methods. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, showed a universe whose geometry was consistent with a large amount of dark energy. Surveys of large-scale structure, the distribution of galaxies across the sky, showed patterns that matched a universe with dark energy. The supernova result was not an isolated anomaly. It was the first glimpse of a larger picture. In 2011, the Nobel Prize in Physics was awarded for the discovery. Half went to Saul Perlmutter. The other half was shared by Brian Schmidt and Adam Rees. The citation recognized the discovery of the accelerating expansion of the universe through observations of distant supernovas. It was a quiet acknowledgement of a result that had, in a sense, been hiding in plain sight. The supernovas, those brief, brilliant deaths of white dwarf stars, had been telling us something for billions of years. We just needed to learn how to listen. Let the image of a Type 1a supernova sit in your mind for a while. A white dwarf, dense and hot, slowly pulling gas from a companion star. For millions of years the mass builds, the pressure grows, and then, in a matter of seconds, carbon fusion ignites. The star is torn apart. For a few weeks, it shines with the light of billions of suns, and then it fades. The light travels outward, across millions or billions of light years, carrying with it a record of the distance it has crossed. Some of that light fell onto the mirrors of telescopes on Earth in the 1990s. It was captured by electronic detectors, converted into data, analyzed by teams of scientists working late into the night, and from that faint, ancient light, we learned that the universe is doing something we never expected. It is pushing itself apart, faster and faster, against the pull of all the matter it contains. This is a strange thought. Every galaxy we can see is moving away from us. The space between us and them is stretching, and the rate of that stretching is increasing. The universe is not just getting larger. It is getting larger at an ever-growing rate. The force responsible, whatever it is, does not weaken as space expands. It seems to be built into the fabric of space itself. As new space is created by the expansion, more of this force comes with it. The more the universe expands, the more dark energy there is. The more dark energy there is, the faster the expansion becomes. It is a feedback loop, a gentle runaway, that has been building for billions of years. We happen to live in a particular moment in cosmic history. For the first several billion years after the Big Bang, the expansion was actually slowing down, just as astronomers expected. The gravity of matter, both ordinary and dark, was dominant. The universe was dense, and gravity had the upper hand. But as the universe expanded, the density of matter dropped. Space grew, matter spread out, and gravity weakened. Dark energy, on the other hand, did not dilute. Its density appears to be constant. So as matter thinned, dark energy remained. Eventually, about 5 or 6 billion years ago, dark energy overtook matter as the dominant influence on the expansion. The deceleration stopped. The acceleration began. We live in the acceleration era. The universe has been speeding up for roughly the last half of its history. Think about that. 5 or 6 billion years ago, just before the acceleration began, the Earth did not yet exist. The solar system had not yet formed. The universe was still slowing down, still feeling the grip of its own gravity, still building the great structures of the cosmic web. And then, quietly, the balance tipped. The push began to win over the pull. The expansion began to speed up. And it will continue to speed up, as far as we can tell, forever. The galaxies will move farther and farther apart. The voids will grow emptier. The distant universe will fade from view. This is the long, slow future that dark energy is shaping, a future of increasing isolation, of cooling, of stretching. Not a sudden end, but a gradual thinning, a quiet dispersal. We will talk more about what dark energy might actually be in the next section. The cosmological constant, the quintessence, the ideas that physicists have proposed, and the questions that remain open. But for now, it is enough to sit with the discovery itself. 2 teams of astronomers, competing and cooperating, spent years chasing the faint light of dying stars. They set out to measure the deceleration of the universe. They found acceleration instead. They checked their work. They published their results. and the world's understanding of the cosmos shifted. The discovery of the accelerating expansion is a reminder that the universe does not conform to our expectations. We thought we knew the story. Big Bang, expansion, gradual slowing, maybe a final crunch or a long coast into darkness. The story was simple. The story was wrong. The universe had a different chapter in mind, a chapter we are still struggling to read. The supernovas told us something new, something that no one had predicted. And now we are left with the question: what is pushing space apart? What is dark energy? The answer, when it comes, may be as strange as the discovery itself, but that is for later. For now, let the distant supernovas glow faintly in your mind, little beacons of destruction and knowledge, scattered across the deep, telling us that the universe is not what we thought. The light from those explosions traveled billions of years to reach us, and in its dimness, it carried a message. The universe is accelerating. We are still learning what that means. We are still learning what the acceleration means. The supernovas told us that the universe is speeding up, but they did not tell us why. They gave us a measurement, not an explanation, and so we arrive at the same place we arrived with dark matter. A name for something unknown, a label for a mystery. Dark energy. The name was chosen to echo dark matter, but the two are very different. Dark matter pulls things together. It clumps. It forms halos and filaments and the scaffolding of the cosmic web. Dark energy pushes things apart. It smooths. It stretches. It drives the expansion of the universe to go faster and faster. They share the word dark because they share the quality of being invisible, undetected except through their gravitational effects. But they are not the same thing. They are not even necessarily the same kind of thing. Dark matter is thought to be a substance, a particle or a field that clusters under gravity. Dark energy is thought to be a property, something built into the fabric of space itself. Or perhaps it is a new force, a field that changes over time. We do not know, and so we name it, and we explore the possibilities, one by one, quietly and carefully. The leading idea for what dark energy might be has a name that sounds technical, but has a long history. It is called the cosmological constant. The term goes back to Albert Einstein. In 1917, a century before the acceleration was discovered, Einstein had just published his general theory of relativity, the theory that describes gravity as the curvature of space and time. He was applying his equations to the universe as a whole, trying to build a model of the cosmos. At the time, the received wisdom among scientists was that the universe was static, eternal and unchanging. The stars moved, but the overall framework of space was fixed. Einstein's equations, however, did not produce a static universe. They produced a universe that either expanded or contracted. Gravity in the equations would pull everything together. A static universe was unstable. It would collapse under its own weight. Einstein saw this as a problem. He trusted the prevailing view that the universe was static. So he added a term to his equations, a small fudge factor, to balance gravity and keep the universe from collapsing. He called it the cosmological constant. In the equations, it acted as a kind of repulsive force, a pressure that pushed outward, counteracting the inward pull of gravity. If you tuned the constant just right, you could get a static universe. The constant was not motivated by any deep principle. It was a patch, a mathematical fix to make the equations match the assumed reality. Then came the discovery of the expanding universe. In the 1920s, Edwin Hubble and others showed that galaxies are moving away from us. The universe is not static, it is expanding. Einstein, confronted with the evidence, abandoned the cosmological constant. He reportedly called it his greatest blunder. He did not need it anymore. If the universe was expanding, the equations worked without the extra term. The cosmological constant was set aside, a curiosity in the history of physics, a wrong turn that had been corrected. But the idea did not die. The cosmological constant, in the mathematics of general relativity, is not just a fudge factor. It has a physical meaning. It represents the energy of empty space. In quantum mechanics, empty space is not truly empty. It is a sea of virtual particles, popping into existence and vanishing again on timescales so short they cannot be directly observed. This vacuum energy, as physicists call it, should have a gravitational effect. And in Einstein's equations, the energy of the vacuum acts just like a cosmological constant. It pushes. It creates a repulsive force that drives expansion. When astronomers discovered in 1998 that the universe's expansion is accelerating, the cosmological constant came roaring back. The acceleration looked exactly like the effect of a positive cosmological constant, the energy of empty space pushing the universe apart. This is, in some ways, a satisfying explanation. It is simple. It uses existing physics, the same equations Einstein wrote down a century ago. The cosmological constant is a single number, a fixed value, that describes the energy density of the vacuum. It is the same everywhere, at all times. It does not change as the universe expands. It is built into the fabric of space. As space grows, more vacuum is created, and with it, more of this repulsive energy. The expansion feeds on itself. The cosmological constant is the simplest model for dark energy, and so far, every measurement we have made is consistent with it. The data from supernovas, from the cosmic microwave background, from the large-scale structure of galaxies, all fit a universe with a cosmological constant. But there is a problem, a very large problem. When physicists calculate how large the cosmological constant should be, using the principles of quantum mechanics and our best understanding of particle physics, the number they get is wrong. Not just a little wrong, catastrophically wrong. The predicted value is about 10 to the power of 120 times larger than the measured value. That is a 1 followed by 120 zeros. It is the largest discrepancy between theory and observation in all of science. If the vacuum energy were as large as quantum mechanics suggests, the universe would have ripped itself apart long before galaxies could form. The cosmological constant we measure is tiny, almost zero, but not quite zero. Why it is so small, but not exactly zero, is one of the deepest puzzles in physics. It is sometimes called the cosmological constant problem. The name is dry, but the mystery is vast. We do not know why empty space has the energy it does. We do not know why it is not vastly larger, or exactly zero. The number is what it is, and we have no satisfying explanation for it. Because of this problem, some physicists have explored other possibilities for dark energy. Maybe the cosmological constant is not constant. Maybe dark energy is a field, something that changes over time and space. This class of ideas goes by the name quintessence. The word is borrowed from ancient philosophy, where it meant a fifth element, a pure substance beyond earth, air, fire, and water. In modern physics, quintessence is a hypothetical field that fills the universe and has negative pressure, driving the acceleration. Unlike the cosmological constant, a quintessence field can change. Its strength can vary from place to place and from era to era. In some models, quintessence was weaker in the past and is growing stronger now. In others, it oscillates. In others still, it will eventually fade, and the acceleration will stop. Quintessence is an interesting idea, but it has no direct evidence. The current data is consistent with a simple cosmological constant. The measurements are not precise enough to tell whether dark energy is truly constant or slowly changing. Future surveys, using new telescopes and new techniques, may be able to test this. They will map the expansion history of the universe with greater precision, looking for any deviation from the constant model. If dark energy is quintessence, the expansion history will show subtle wiggles, small departures from the straight line of a cosmological constant. As of now, no such wiggles have been seen. The cosmological constant remains the simplest and best-fitting model, but the search continues. There are other ideas, more speculative still. Some physicists have suggested that the acceleration is not driven by a new form of energy at all, but by a modification of gravity. Perhaps Einstein's theory of general relativity is not quite right on the largest scales. Perhaps gravity weakens differently than we think across cosmic distances, and the apparent acceleration is a mirage caused by our misunderstanding of gravity. These ideas are sometimes called modified gravity theories. They are harder to make consistent with the full suite of observations, but they are not ruled out. The field is open. The question is unsettled. It is important to say plainly that no one knows what dark energy is. The cosmological constant is the leading candidate, but it comes with a deep theoretical puzzle. Quintessence is a plausible alternative, but it has no direct support. Modified gravity is a possibility, but it struggles to explain all the data. We have a name for the thing, but the name is just a placeholder. Dark energy is the label on a locked box. We have measured the size and shape of the box. We know it accounts for about 68% of the total energy in the universe. We know it started dominating the expansion about 5 or 6 billion years ago. We know it is smooth, not clumpy like dark matter. It does not gather in galaxies or clusters. It is everywhere the same, as far as we can tell, but we do not know what is inside the box. The box remains closed. There is a certain calm in this not knowing. The universe has given us a new puzzle, and we are not yet ready to solve it. That is fine. Science is not a race to answers. It is a process of narrowing uncertainties, of asking sharper questions, of learning to live with the open space between what we measure and what we understand. Dark energy is that open space. It is the largest single component of the universe, and we do not know what it is. The people who study it, the cosmologists and the theorists, are not alarmed by this. They are patient. They build their instruments, and they refine their models, and they wait. The universe is not in a hurry, and neither are they. Let the idea of the cosmological constant sit for a moment. Empty space is not empty. It has energy. That energy pushes. It pushes on every point in the universe, equally, in all directions. It does not weaken as the universe expands. It is a property of space itself. As new space comes into being, more energy comes with it. The push grows. The acceleration continues. This is the simplest picture. It may be the right one, or it may be too simple. Empty space may hold secrets we have not yet dreamed of. The vacuum may have a structure, a dynamics, a history. It may be richer than a single unchanging number. We do not know. And that not knowing is, in its own way, a kind of answer. It tells us that the universe is not finished surprising us. It tells us that our understanding is incomplete. It tells us that there is more to learn. As you lie here, you might think about the emptiness around you. The space between your body and the ceiling. The space between the Earth and the Moon. The space between our galaxy and the next. All of it, every cubic centimeter of it, is filled with dark energy, if the cosmological constant model is correct. The energy is incredibly dilute. You cannot feel it. It does not push on your skin or move objects around the room. Its effects are only visible on the largest scales, across billions of light years. But it is there, if the theory is right, a steady hum of repulsion in the fabric of reality. The voids between galaxy clusters are growing because of it. The cosmic web is being stretched. The universe is thinning out. And the energy that drives this process is the same energy that Einstein once proposed, then abandoned, then watched return from the grave of discarded ideas to become the centerpiece of modern cosmology. The story of the cosmological constant is a story of humility. An idea, rejected by its creator, turned out to be essential. The universe did not care about Einstein's blunder. The universe had its own plans. The next step in our story is to bring everything together, dark matter and dark energy, the pull and the push, the 5% of ordinary matter, the 27% of dark matter, the 68% of dark energy, the proportions of everything. That is for the next section. For now, we sit with the open question. What is dark energy? A constant, a field, a modification of gravity. We do not know, And the honesty of that statement is part of the calm. We are not required to have all the answers. We are only required to keep looking, keep measuring, keep asking. The dark energy does not mind being unknown. It has been pushing the universe apart for billions of years. A few more decades of human puzzlement will not trouble it at all. We have been talking for a while now about the invisible, about dark matter, the unseen mass that holds galaxies together and built the cosmic web, about dark energy, the unknown force that pushes the universe apart, about the search for particles that might be streaming through us at this very moment, and about the quiet, patient astronomers who measured the spins of galaxies and the brightness of distant exploding stars. All of these threads lead to a single, simple picture, a cosmic budget, a breakdown of what the universe is made of, the proportions of everything. This picture did not come from a single observation. It came from bringing together many different kinds of measurements, made over decades, by different teams using different instruments. The flat rotation curves that Vera Rubin measured, the bent light around colliding galaxy clusters, the computer simulations of cosmic structure formation, the accelerating expansion revealed by distant supernovas, and one more piece of evidence that we have not yet spent much time with, the faint afterglow of the early universe, a wash of light that fills all of space. It is called the cosmic microwave background, and it is one of the most important sources of information cosmologists have. Let the name sit for a moment. The cosmic microwave background. It is a kind of light, but not the kind your eyes can see. It is microwave radiation, the same general type of radiation that heats food in a microwave oven, though far, far fainter. This light is not coming from any star or galaxy. It is coming from the early universe itself. It is the oldest light in existence. To understand it, we need to go back to a time about 380,000 years after the Big Bang. Before that time, the universe was so hot and dense that atoms could not form. Electrons and protons moved freely, and they scattered light constantly. The universe was a fog. Light could not travel far without bumping into a free electron. It was trapped, bouncing around in the hot plasma like a fly in a jar. Then, as the universe expanded and cooled, it reached a temperature where electrons and protons could combine to form neutral atoms. This is the moment cosmologists call recombination, though the name is a little misleading because the particles had never been combined before. It was the first combination. When the free electrons were taken up into atoms, the fog cleared. Light could suddenly travel freely. The universe became transparent, and the light that was present at that moment, the light of the hot, dense early universe, has been traveling ever since. For nearly 13.8 billion years, it has been streaming through space, stretched by the expansion of the universe. What was once visible light, the glow of a hot fog at about 3,000 degrees, has been stretched into microwaves. The temperature of this light today is just about 2.7 degrees above absolute zero. It is a cold, faint whisper of the hot beginning. The cosmic microwave background was first detected by accident in 1964 by two radio astronomers, Arno Penzias and Robert Wilson. They were working with a sensitive radio antenna in New Jersey and found a persistent background noise that they could not explain. They checked their equipment. They cleaned pigeon droppings out of the antenna. The noise remained. It came from every direction in the sky. It was the cosmic microwave background. They had stumbled upon the afterglow of the Big Bang. They won the Nobel Prize for their discovery. But the cosmic microwave background is not perfectly smooth. It has tiny variations in temperature from one part of the sky to another. These variations are minuscule, differences of about 1 part in 100,000, but they are the imprint of the tiny density ripples in the early universe, the seeds of all later structure. Regions that were slightly denser appear slightly warmer in the microwave background. Regions that were slightly less dense appear slightly cooler. The pattern of these hot and cold spots tells us an enormous amount about the universe. It tells us about its age, its geometry, its expansion rate, and its composition. Space missions have mapped these temperature variations with increasing precision. The COBE satellite, the Cosmic Background Explorer, made the first all-sky map in the early 1990s. The WMAP satellite, the Wilkinson Microwave Anisotropy Probe, made a much more detailed map in the early 2000s. And the Planck satellite, launched by the European Space Agency, made the most precise map to date, releasing its final results in 2018. The Planck data is the gold standard. It is the sharpest picture we have of the universe at the moment it became transparent. What does the cosmic microwave background tell us about the proportions of the universe? The pattern of hot and cold spots is shaped by sound waves that rippled through the early universe, back when it was a hot plasma. These sound waves, called baryon acoustic oscillations in technical language, created a characteristic scale in the temperature map. There is a preferred size for the hot and cold spots. By measuring that size, cosmologists can determine the geometry of the universe. The spots appear a certain angular size on the sky. That size depends on whether space is flat, curved like a sphere, or curved like a saddle. The measurement shows that the universe is flat, or very close to it. The geometry of space on the largest scales is Euclidean. Parallel lines stay parallel. Triangles add up to 180 degrees. A flat universe has a specific total energy density. That total density, in the language of general relativity, is called the critical density. The cosmic microwave background tells us that the universe's total energy density is equal to the critical density, within a small margin of error. But the cosmic microwave background also tells us something else. It tells us how much of that density is in the form of ordinary matter. The height of the peaks in the temperature map, the relative brightness of the hotspots at different angular scales, is sensitive to the amount of ordinary matter. Ordinary matter, the protons and neutrons and electrons that make up atoms, interacts with light. Dark matter does not. The cosmic microwave background can distinguish between the two by the way the sound waves propagate. The measurement gives a value. Ordinary matter makes up about 5% of the total energy density of the universe, just 5%. This number, from the cosmic microwave background, aligns with other measurements. The abundances of light elements like hydrogen, helium, and lithium, forged in the first few minutes after the Big Bang, also point to a universe with about 5% ordinary matter. The two methods agree. 5% is the cosmic budget for stars, planets, gas, dust, and people. Everything made of atoms. Everything on the periodic table. Everything we have ever seen or touched or measured in a laboratory. 5%. But the cosmic microwave background also tells us that the total amount of matter, ordinary plus dark, is about 32% of the critical density. So if ordinary matter is 5%, then dark matter must be about 27%. The difference between the total matter density and the ordinary matter density is the dark matter density. 27%. More than 5 times as much dark matter as ordinary matter. The dark matter that Zwicky first glimpsed in the Coma cluster, that Rubin mapped in her flat rotation curves, that bends light around colliding clusters, that forms the scaffolding of the cosmic web. It accounts for 27% of everything. And the rest? If the total energy density of the universe is 100% of the critical density, and matter of all kinds adds up to about 32%, then the remaining 68% must be something else. Something that is not matter at all, something that does not clump, something that is smooth and constant and pushes space apart. That something is dark energy, 68%, the largest single component of the universe, the dominant ingredient in the cosmic recipe. Dark energy, discovered through the dimness of distant supernovas, confirmed by the cosmic microwave background, reinforced by the large-scale structure of galaxies. All of these independent lines of evidence converge on the same numbers, about 5% ordinary matter, about 27% dark matter, about 68% dark energy. Let these numbers settle. They are worth sitting with. The universe, in its entirety, is dominated by things we cannot see and do not understand. The ordinary matter that makes up the visible world, the stars and planets and galaxies that fill the images from our telescopes, is a small fraction, a rounding error, a thin frosting on a vast, dark cake. We are not the main event. We are not even a significant minority. We are a tiny, luminous afterthought in a universe built from invisible things. This is a humbling realization. It is also, in a quiet way, a beautiful one. The universe is not limited by what our eyes can see or what our instruments can directly detect. It is richer and stranger than our everyday experience would suggest. The fact that we can measure these proportions at all, that we can deduce the existence and the amount of things we cannot see, is a testament to human curiosity and care. Zwicky with his cluster, Rubin with her rotation curves, the lensing maps of the bullet cluster, the supernova hunters of the 1990s, the teams that built and flew the Planck satellite. Each measurement was a small, careful step. Each depended on the work of many people over many years. And together they have given us a picture of the universe that no single observation could have provided, a picture that is both precise and deeply mysterious. We know the proportions. We know that ordinary matter is 5%. We know that dark matter is 27%. We know that dark energy is 68%. But knowing the proportions is not the same as understanding the ingredients. We know what ordinary matter is. We do not know what dark matter is. We do not know what dark energy is. The numbers are precise, but the names are placeholders. Dark matter and dark energy are labels for our ignorance. They are the cosmic I don't know, written in the language of percentages and energy densities. This is the state of modern cosmology, a precise ignorance, a well-measured mystery. We have weighed the universe, we have tallied its contents, and the tally tells us that 95% of everything is unknown. This is not a failure. It is an invitation. It is the starting point for the next century of inquiry. The questions are clear. What particle makes up dark matter? What is the nature of dark energy? Why are the proportions what they are? We do not have the answers, but we have the questions, sharpened and refined by decades of careful observation. As you lie here, you might think about the 5%. That small slice of the cosmic pie is everything you have ever known. The bed beneath you, the air in your lungs, the stars in the night sky, the distant galaxies in the Hubble images, your own body, with its bones and blood and the quiet electrical impulses of your brain. All of it is ordinary matter. All of it is part of the 5%. And yet, for most of human history, we thought this 5% was all there was. We had no reason to suspect the other 95. The night sky looked complete. The stars seemed sufficient. It took generations of careful, patient work to reveal the larger reality, the dark matter halo holding our galaxy together, the dark energy stretching the space between us and our neighbors, the vast unseen majority. There is a kind of peace in knowing how small our slice is. It puts our worries and our urgencies into a wider context. The universe is mostly made of things we cannot touch or see, and yet we are here, briefly, thinking about it. That is a strange and lovely thing, a small part of the 5%, aware of the other 95, a flicker of consciousness in a dark cosmos. The proportions of everything are not a cause for alarm, they are a cause for quiet wonder. The universe is larger and stranger than we knew, and we are lucky enough to be able to know it, even a little. The next section will turn to the things we still do not know, the tensions in our measurements, the disagreements that hint at new physics, the honest, open questions that remain. But for now, we sit with the numbers. 5%, 27%, 68%, the proportions of everything, a cosmic recipe for a universe mostly dark, mostly silent, mostly unknown. And yet, somehow, home. We have arrived at the proportions. 5% ordinary matter, 27% dark matter, 68% dark energy. The numbers are precise, but they are also humbling. They tell us that most of the universe is made of things we cannot yet explain. And so now, in this quiet moment before the end, we turn to the open questions, not to answer them, but to sit with them, to let them be what they are, genuine uncertainties, honest gaps in our knowledge, the things we still do not know. There is a tendency, in stories about science, to wrap things up neatly, to present a mystery and then resolve it, leaving the listener with a sense of closure. But the universe does not work that way. Every answer opens new questions, every measurement sharpens the edges of what we do not understand, and that is not a problem to be fixed. It is the natural state of a curious species looking out at a vast and complicated cosmos. The not knowing is not a failure, it is part of the story. It is where the next discoveries will come from. One of the most interesting open questions in cosmology right now goes by a name that sounds a little dramatic, but the idea behind it is simple. It is called the Hubble tension. The name refers to a disagreement, a tension, between two different ways of measuring how fast the universe is expanding. The expansion rate is called the Hubble constant, after Edwin Hubble, who first measured it. The Hubble constant tells you how fast a galaxy at a given distance is moving away from us. It is a single number that describes the current speed of cosmic expansion. Measuring that number accurately has been a goal of astronomy for nearly a century, and now, with modern instruments and methods, we can measure it in two completely different ways. The problem is that the two measurements do not agree. The first method looks at the early universe. It uses the cosmic microwave background, the faint afterglow we talked about earlier. The Planck satellite mapped the temperature variations in the microwave background with great precision. The pattern of those variations depends on the properties of the universe, including its expansion rate. By fitting a model to the data, cosmologists can extract a value for the Hubble constant. The Planck measurement gives a number. Written out in full, it is about 67.4 kilometers per second per megaparsec. That unit, kilometers per second per megaparsec, means that a galaxy 1 megaparsec away, about 3.26 million light-years, is moving away at about 67.4 kilometers per second. A galaxy twice as far moves away twice as fast. That is the Hubble law. The Planck value is very precise. It comes from a model of the early universe, and it assumes that the model, the standard cosmological model with dark matter and dark energy, is correct. The second method looks at the late universe. It uses direct observations of galaxies and supernovas. Astronomers measure the distances to faraway galaxies using standard candles, like the Type Ia supernovas we discussed, and they measure their redshifts. By combining many such measurements, they can build a ladder of distances that reaches from the local universe out to billions of light-years. This distance ladder method is independent of the early universe model. It does not assume anything about the cosmic microwave background or the standard cosmological model. It simply measures distances and speeds and calculates the expansion rate directly. The most precise distance ladder measurements give a Hubble constant of about 73 kilometers per second per megaparsec, a higher number. The universe, measured this way, is expanding faster. The difference between the two numbers is not large in absolute terms. About 67 versus about 73, but the error bars on each measurement are small enough that the two values do not overlap. They disagree at a statistically significant level. The chance that the difference is just a random fluke is now very small. Something is going on. Either one of the measurements has an unknown error, or the two methods are measuring different things because the universe does not behave as our models predict. Perhaps the early universe model is missing something. Perhaps the distance ladder has a systematic bias no one has identified. Or perhaps the Hubble tension is a real signal, a clue that points to new physics, something beyond the standard cosmological model, a new particle, a new behavior of dark energy, a modification of gravity. We do not know. The Hubble tension is a good example of how science works at the frontier. When measurements disagree, it means there is something to learn. The disagreement is not a crisis. It is an opportunity. Many teams of astronomers and cosmologists are working on the problem right now. They are refining the distance ladder, using new standard candles like red giant stars and water masers. They are reanalyzing the Planck data. They are exploring models that could bridge the gap. The tension may resolve with better data, converging on one value or the other. Or it may persist, forcing a revision in our understanding. Either outcome is progress. Either outcome is science doing what science does. But for now, the tension is unresolved. We have two measurements of the expansion rate, and they do not agree. That is an honest statement of the current situation. And the Hubble tension is not the only open question. There is also the nature of dark matter. We have spent a long time talking about it. The evidence from rotation curves, from gravitational lensing, from the cosmic microwave background, from structure formation, the evidence is strong and cross-validated. But the evidence tells us only that dark matter is there, and roughly how much of it there is, and how it is distributed. It does not tell us what dark matter is made of. We have ruled out ordinary matter in dim forms. We have searched for WIMPs, the weakly interacting massive particles, with detectors deep underground. We have searched for axions with sensitive radio receivers. We have looked for sterile neutrinos and primordial black holes. So far, none of these searches has found a clear, unambiguous signal. The dark matter particle, if it is a particle, remains undetected. It is possible that dark matter is something else entirely, something we have not yet thought of. It is possible that our understanding of gravity needs modification, though this idea has grown harder to sustain. The honest answer is that we do not know what dark matter is. The evidence tells us it exists. The searches have not yet found its nature. That gap is real, and it is large, and it is one of the central questions in modern science. And then there is dark energy. We know even less about dark energy than we do about dark matter. We know it makes up about 68% of the universe. We know it drives the acceleration of the expansion. We know it is smooth, not clumpy. It does not gather in galaxies or clusters. It appears to be the same everywhere and at all times. The simplest model, the cosmological constant, fits the data well. But the cosmological constant comes with its own deep puzzle. The predicted value, from quantum mechanics, is vastly larger than the measured value. Why is the cosmological constant so small? Why is it not zero? Is it truly constant, or does it change over time? Could it be a new kind of field, like quintessence? Could it be a sign that general relativity breaks down on the largest scales? We do not know. Dark energy is the biggest single component of the universe, and it is also the most mysterious. Its nature is an open question, as open as any question in physics. Let these uncertainties sit for a moment. The Hubble tension, the nature of dark matter, the nature of dark energy. Three large, unresolved questions at the heart of modern cosmology. Together they cover the past, present, and future of the universe. The Hubble tension touches the expansion history, the story of how space has grown over time. Dark matter touches the structure of the cosmos, the way matter clumps and gathers into galaxies and clusters. Dark energy touches the ultimate fate of the universe, the long, slow acceleration into an ever emptier future. On all three fronts, we have made remarkable progress in measurement. We have mapped the cosmic microwave background to exquisite precision. We have weighed the universe. We have traced the cosmic web. We have watched distant supernovas and measured their dim light. But the measurements have led us to questions we cannot yet answer. That is the state of the field. Precise, but incomplete. Successful, but unfinished. This is not a disappointing place to be. It is an exciting one, in a quiet way. The open questions are not failures. They are the engine of future discovery. Every generation of scientists inherits a set of questions from the generation before. The questions we have now are sharper and more specific than the questions Zwicky and Rubin faced. They knew something was missing. We know the percentages. We know the shape of the missing mass. We know the acceleration history. We have narrowed the field. The next step, the identification of the dark matter particle, or the understanding of dark energy, may take decades. It may take centuries. It may require new instruments, new theories, new ways of thinking. That is fine. The universe is not going anywhere. It will still be here, expanding and clumping and accelerating, waiting for us to figure it out. As you lie here, you might think about what it means to live in an age of such precise uncertainty. We know enough to ask good questions. We do not yet know enough to answer them. That is a privilege. It means we are part of the search. We are not at the end of the story. We are in the middle of it. The middle is where the work happens. The middle is where the patience is required. The middle is where we sit with the numbers and the tensions and the open possibilities, and we keep looking. The next section will be the last. A quiet, drift-off close. A return to the image of lying beneath a sky that is mostly made of things we cannot see or name. But for now, we stay with the not knowing. The honest, open uncertainty, the Hubble tension, the dark matter particle still unfound, the dark energy still unnamed. These are not problems to solve tonight. They are the landscape of the unknown, spread out before us like the dark spaces between stars. They do not demand resolution, they simply are, and we, lying here in the quiet, can let them be. The universe does not mind being mysterious. It has been mysterious for all of human history. A little more time, while we sharpen our questions and build our detectors, and wait for the faintest of signals, will not trouble it at all. The not knowing is part of the calm. It is part of the night. It is part of what makes the stars, when we do see them, so worth looking at. The not knowing is part of the calm. It is part of the night. And now, as we reach the final quiet moments of this telling, we can let the mystery be what it is. A companion, not a problem. A presence, not a puzzle to be forced into shape. We have traveled a long way together through the dark, from Zwicky's cluster of galaxies, racing too fast to be held by the visible stars, from Vera Rubin's flat rotation curves, those stubborn lines that refuse to drop, from the bent light around the bullet cluster, tracing the shape of invisible mass, from the deep caverns where detectors sit in liquid xenon, waiting for a single atom to twitch, from the distant supernovas, dimmer than they should be, whispering that the universe is not slowing down but speeding up, from the faint afterglow of the Big Bang, the cosmic microwave background, telling us the proportions of everything. All these threads, all these careful measurements, all these generations of patient work have led us to a single, quiet realization. We are a small part of something much larger, and most of that larger something is unknown. Lie back now, if you have not already. Let your body sink into whatever holds it, the mattress, the cushion, the floor, the ground. Feel the weight of yourself, the ordinary matter of your bones and muscles, pressing down. That weight, that solidness, is made of atoms. Protons and neutrons and electrons. The same stuff that makes up stars and planets and galaxies. The same 5%. The rest of you, the space between those atoms, is mostly empty. And passing through that emptiness, right now, are particles of dark matter, if dark matter is made of particles. They do not bump into you, they do not warm you, they do not leave a trace. They are simply there, as they have been for billions of years, passing through the earth and through the sun, and through the spaces between galaxies. You are swimming in an invisible sea, even here, even now, in the quiet dark of your room. And beyond that, beyond the dark matter halo of the Milky Way, beyond the local group of galaxies, beyond the great filaments of the cosmic web, space itself is stretching. The voids between clusters are growing. The distant galaxies are moving farther away. And the rate of that stretching is increasing, driven by something we still cannot name: dark energy, the cosmological constant, quintessence. Whatever it is the dominant force in the universe today. The push is stronger than the pull. The scattering is winning over the gathering. The universe is thinning out, slowly, across billions of years, heading toward a future that is colder and darker and emptier than the present. That is not a sad thought. It is simply the long, slow arc of cosmic history. The universe does not owe us permanence. It gives us this moment. This brief, warm moment when the stars are still shining and the galaxies are still close enough to see, and we are here, thinking about it. Think about that. Think about what it means to be a part of the 5% that can look out and wonder about the other 95. The universe has made a strange thing. It has made matter that can think, matter that can build telescopes and spectrographs and satellites, matter that can measure the spins of distant galaxies and the brightness of exploding stars, matter that can map the afterglow of its own beginning. All of that curiosity and patience and care is the work of ordinary matter, the 5%, the small slice, the thin frosting on the cosmic cake, and that small slice has managed to learn something remarkable. It has learned that it is not alone, that it is surrounded, penetrated, shaped, and driven by invisible things. Dark matter, dark energy, the unseen majority. The universe has become aware of its own darkness, through us. This is a comforting thought, in its way. We are not separate from the universe, we are a part of it. The same atoms that make up your body were forged in stars that lived and died long before the Earth was born. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it was cooked in the nuclear furnaces of ancient suns and scattered across space when those suns exploded. You are made of stardust, as the saying goes, and you are also made of the 5%, the rare, luminous fraction of reality, the part that can see, the part that can ask. And the dark matter, the 27%, is not separate from you either. It is here. It is holding the galaxy together. Without it, the Milky Way would never have formed. The sun would never have ignited. The Earth would never have coalesced from the disk of gas and dust around the young sun. Life would never have arisen. You are here, in a very real sense, because of dark matter. The invisible scaffold built the stage on which the visible world could appear. We owe our existence to something we cannot see and do not understand. That is a strange kind of kinship, a connection to the unknown. You are held, right now, by the gravity of something invisible, something that has been here since the beginning, something that will still be here long after the last star has burned out. And the dark energy, the 68%, is shaping the future. It is stretching space. It is carrying the distant galaxies away. Eventually, if the acceleration continues, the universe will become a lonelier place. The galaxies beyond our local group will slip over the horizon, their lights stretched to invisibility. Future astronomers, if there are any, will look out at a sky that is dark and empty, with no evidence of the larger cosmos we can see today. The cosmic microwave background will be stretched to undetectable wavelengths. The evidence for the Big Bang will be gone. The universe will hide its own history. But that is billions of years away. For now, we are in the Golden Age, the age when the universe is old enough to have made stars and planets and people, but young enough that we can still see the evidence of its birth. We are lucky to be here now, lucky to be part of the 5% that gets to see this. Let those thoughts drift now. Let them soften and blur at the edges. You do not need to hold on to them. They are not tasks to complete or facts to memorize. They are just ideas, floating in the dark, keeping you company while you rest. The universe is mostly unseen. Most of it is dark matter and dark energy. The ordinary matter, the stars and planets and people, is a small share. We know the proportions. We do not know the natures. And that is fine. That is the way things are. That is the story, still being written. Outside, whether you can see it or not, the night sky is doing what it always does. The stars are shining. The planets are moving along their slow orbits. The Milky Way is arching across the darkness, a river of light made of hundreds of billions of suns. And around and between and through it all, the dark matter halo holds it steady. And beyond it all, the dark energy pushes the distant galaxies farther away. The great cosmic dance continues. The pull and the push, the gathering and the scattering, the visible and the invisible, moving together across time. You are part of that dance. You have always been part of it. The atoms in your body were there in the early universe. The dark matter was there too. The dark energy was there, quiet and waiting, ready to take over when the time was right. And now you are here, breathing slowly, listening to a voice in the dark talk about things that cannot be seen. That is a strange and lovely thing, a small miracle of the 5%, a moment of awareness in a vast and mostly dark cosmos. There is no need to remember any of this. There is no need to hold on to the names or the numbers. Fritz Zwicky, Vera Rubin, the bullet cluster, the Hubble tension, the cosmological constant. They will all be here tomorrow, if you want to find them. But for now, let them go. Let them dissolve into the quiet. The universe will not mind. It has been waiting for billions of years. It can wait a little longer while you sleep. Feel your breathing slow. Feel the weight of your body settle. The dark matter is passing through you. The dark energy is stretching the space between your atoms, though far too gently to measure. You are held, you are safe, you are part of something vast and strange and mostly unknown, and that is not a problem to solve. It is simply the way things are. The night is deep and the universe is large, and the 5% is small and precious and fleeting, and here you are, in the middle of it, resting. Let the words fade now. Let the silence grow. There is no formal goodbye, because there is no leaving. The universe is still there, still dark and bright and expanding and unknown. You are still there, still breathing, still part of the whole strange story. The only thing left is to rest, to close your eyes, if they are not already closed, to let the thoughts drift like clouds across a night sky, to sink into the quiet that was here long before words, and will be here long after. The dark matter does not mind being unknown. The dark energy does not mind pushing the universe apart. The stars do not mind being outnumbered by invisible things. And you do not need to mind either. You can just be here. You can just breathe. You can just rest. The mystery will still be here when you wake. Patient, quiet, waiting. Like an old friend in the dark.